There is a woman somewhere in England right now who carries something inside her that fewer than 50 people on the entire planet are known to possess. She does not know this. She has never been told. She goes to work, makes tea, maybe watches something on television before bed, and the blood moving quietly through her veins holds a secret that has baffled immunologists, geneticists, and medical historians for decades. If she were ever in a serious accident and needed a transfusion, the wrong blood could kill her within minutes. And the right blood, the only blood that would keep her alive, would have to be sourced from a list so short that hospitals maintain it like a state secret. This is not a hypothetical. It has already happened. People with this blood type have died waiting. Others have survived only because of networks of donors so rare that they span continents, because of medical emergencies coordinated across time zones, because someone picked up a phone at 2 a.m. and called a stranger in Mumbai or Birmingham or Sao Paulo and asked them to donate immediately. The blood type is called Bombay blood, or more precisely, the H-null phenotype, and Britain has more people with it than almost any other country on Earth outside of South Asia. That single fact, quiet as it sounds, is not simple. It is not a coincidence. And the story behind it reaches back further than the National Health Service, further than the British Empire, further than the moment any Briton ever set foot on Indian soil. It reaches into the deep genetic history of populations that have been moving, mixing, separating, and carrying their biology across the world for thousands of years. If you are watching this to fall asleep, that is exactly why I make these videos. Maybe subscribe and let me know where you are right now and what time it is. Most people who know anything about blood type have heard of the ABO system. You are probably A, B, or O. You may know whether you are positive or negative, meaning whether you carry the Rh factor or not. These things feel fundamental. They feel like they explain everything about how blood works. But the ABO system and the Rh factor together are just 2 of over 300 known antigen systems on human red blood cells. 300. Most of them are obscure enough that the average doctor has never had to think about them. Most of them only matter in very specific clinical situations: transfusion medicine, organ transplant, pregnancy complications. But some of them matter in ways that completely upend how we think about human history, migration, and identity. Bombay blood is one of those. It was discovered in 1952 by a physician named Y.M. Bende, working in Bombay, India, which is now called Mumbai. Bende was trying to determine the blood type of a patient, and the results made no sense. The patient appeared to be blood type O, but when Bende tested the blood against standard O-type serum, something went wrong. The cells agglutinated, they clumped, they reacted as if they were foreign, and in a profound sense, they were. The patient did not belong to the standard ABO system at all. There was something missing from the surface of his red blood cells that had always been assumed to be universal. Something so fundamental that, until that moment, nobody had thought to check for its absence. That something is the H antigen. In almost all human beings, the H antigen is the molecular foundation on which A and B antigens are built. It is produced by a gene called phut1, and it appears on the surface of red blood cells before other blood type antigens are added on top of it. If you are blood type A, you have H antigen modified by A. If you are blood type B, you have H antigen modified by B. If you are blood type O, you have H antigen left largely unmodified, which is why O is sometimes called the universal donor. The H antigen is what makes the whole system work. But people with Bombay blood do not produce the H antigen at all. They carry mutations in the FUT, one gene that disable the enzyme responsible for creating it. Their red blood cells are effectively blank on the H antigen front. And because their immune systems have never encountered H antigen, they have developed antibodies against it, which means if you give them blood from a standard blood type O donor, blood that is actually full of H antigen, their immune system will treat it as a devastating foreign invasion. Hemolysis sets in, red blood cells rupture, kidneys can fail. Without rapid intervention, a person with Bombay blood receiving standard blood can die from what was supposed to save them. The only people who can safely donate to someone with Bombay blood are other people with Bombay blood. And globally, the frequency of this phenotype is estimated at roughly 1 in a million. In most of the world, in Britain, and in certain populations linked to specific genetic lineages, the number is considerably higher. Not 1 in a million, closer to 1 in 10,000 in some communities. And the reason why takes us somewhere most people would not expect. You have to start with the gene itself. FUT1 is located on chromosome 19, and it is not the only gene in the story. There is a closely related gene called FUT2, which controls secretor status, meaning whether H antigen gets expressed in bodily secretions like saliva and mucus. People who are non-secretors carry mutations in FUT2 that prevent this. And crucially, the mutations that cause Bombay blood are different depending on where in the world the affected person comes from. The mutation that causes Bombay blood in South Asian populations is not the same mutation that causes it in Japanese populations, not the same as the mutation found in individuals of European or Middle Eastern descent. This tells us something important. Bombay blood did not arise once and then spread. It has arisen multiple times, independently, in different populations, as a result of different mutations striking the same gene in different places and different eras. This is called convergent evolution at the molecular level, and it is the first hint that the story of Bombay blood is not really a story about a single event or a single people. It is a story about a specific kind of biological vulnerability that appears, persists, and concentrates in populations under the right conditions. And those conditions, it turns out, are deeply tied to history in ways that take a long time to fully absorb. In South Asia, the FUT1 mutations that cause Bombay blood have been tracked most extensively in populations from the Indian subcontinent, particularly from Maharashtra, the western Indian state where Mumbai is located. Bende's original discovery happened there for a reason. The genetic variants that suppress H antigen production are present in that population at elevated frequencies compared to the global baseline. But elevated does not mean common. Even in Maharashtra, the phenotype appears in roughly 1 in 10,000 people, sometimes more in certain subpopulations, sometimes less. It is still rare by any measure. But compared to the global rate of 1 in a million, it is dramatically, meaningfully higher. What drove these frequencies up in specific South Asian populations is not entirely known. Genetic drift is one explanation. When a population remains relatively small and isolated for many generations, rare mutations can rise to higher frequencies simply through chance. The FUT1 mutations may have been present at low levels in ancestral South Asian populations and drifted upward in specific groups that underwent periods of reduced gene flow. Founder effects are another possibility. If a small group of founders carried the mutation and then expanded into a larger population, carrying their unusual genetics with them, the frequency in that descended population would be higher than in the broader environment from which the founders came. But there may be something else. Some researchers have speculated, though it remains speculative, that the absence of H antigen might confer some selective advantage against specific pathogens. There is a body of literature suggesting that blood-type antigens, including H antigen, can be exploited by certain bacteria and parasites as molecular hooks for attachment and infection. If the presence of H antigen makes someone slightly more vulnerable to a particular infectious disease that was historically prevalent in a region, then individuals lacking H antigen might have survived and reproduced at marginally higher rates, slowly nudging the mutation upward in frequency over many generations. This is the same logic used to explain the high frequency of sickle cell trait in malaria endemic regions. Not that the mutation is harmless, because in Bombay blood it clearly carries serious transfusion risks, but that the trade-off might have favored its persistence under certain ecological conditions. None of this is proven for Bombay blood, but it is the kind of mechanism that genetic epidemiologists keep in mind when a rare variant appears at unexpectedly elevated frequencies in a geographically specific population. There has to be a reason. Population genetics does not usually produce anomalies without causes. And the deeper you dig into why Bombay blood concentrates where it does, the more you realize that the answer is always the same kind of answer: movement, history, contact, and isolation. The long, slow, often painful negotiation between populations across time. Which brings us to Britain. The story of Bombay blood in Britain is inseparable from the story of South Asian migration to the United Kingdom. That migration did not begin when the first ships docked in Southampton in the late 1940s and 1950s, though that is where most people's mental timelines start. It does not begin with the arrival of Commonwealth citizens after partition, or with the economic migration of the 1960s and 1970s, or with the Ugandan Asian expulsions of 1972. Those are chapters in a much longer book. And the book opens much earlier, in ways that are both obvious and surprising, and that carry genetic consequences still visible in British blood banks today. The first documented South Asian individuals in Britain appear in historical records dating back to the late 16th and early 17th centuries. These were predominantly servants and sailors, people brought to England by merchants and aristocrats who had interests in the East India trade. The East India Company was founded in 1600, and almost from its earliest years, ships travelling between India and England carried not just goods but people. Lascars, the term used for South Asian and Southeast Asian sailors employed on British merchant vessels, were present in London by at least the 1620s. Many settled permanently. By the late 17th century, there were small but documented communities of South Asian individuals in London, Bristol, and other port cities. These early settlers were overwhelmingly male, poor, and largely invisible to the historical record in any detailed sense. They married into local communities, their descendants blending into the general population of working-class urban England. Whether any of them carried the FUT1 mutations associated with Bombay blood is impossible to know. But they represent the earliest layer of a demographic process that would, over the following 3.5 centuries, bring hundreds of thousands and eventually millions of people with South Asian genetic backgrounds into the British population. The next major wave comes with the solidification of British rule over the Indian subcontinent. By the mid-18th century, the East India Company controlled vast territories. By the mid-19th century, after the Indian Rebellion of 1857, the Crown governed directly. This political reality generated a continuous flow of people between India and Britain, not just goods, not just soldiers, but administrators, lawyers, students, professionals, servants, ayahs, caring for the children of colonial families, princes completing their education at Oxford and Cambridge, reformers and nationalists and intellectuals engaging with British political ideas and bringing those ideas home transformed. Some of these individuals settled permanently. Others came, studied, argued, organized, and returned. The ones who settled added threads to the genetic fabric of Britain. Not many, not yet enough to dramatically alter population-level frequencies of rare blood variants, but enough to establish communities, networks, and the social infrastructure that would support much larger migrations later. The 20th century is where the numbers begin to matter for something like Bombay blood. The partition of British India in 1947 created the states of India and Pakistan amid catastrophic violence that displaced millions of people. The independence that followed the partition, and the British Nationality Act of 1948, which granted Commonwealth citizens the right to live and work in the United Kingdom, opened a channel that hundreds of thousands of people moved through over the following decades. Men came first, largely. Then families followed. Communities built themselves in industrial cities, in the textile towns of West Yorkshire, in the manufacturing districts of the Midlands, in London, in Leicester, in Bradford, in Birmingham. These communities did not come from everywhere in South Asia equally. Migration patterns were shaped by very specific factors. Colonial recruitment networks had drawn men from particular regions, particular castes, particular villages, into military and labor service. Those networks became the channels through which post-war migration flowed. A significant portion of the South Asian migrants to Britain came from relatively limited geographic areas within the subcontinent. From the Mirpur district of what is now Azad Kashmir, from the Sylhet region of what is now Bangladesh, from the Punjab, divided between India and Pakistan at partition, from the Gujarati communities of both Western India and East Africa, the latter group arriving particularly after the East African expulsions of the 1960s and 1970s. This geographic specificity matters enormously for a genetic variant like Bombay blood, If the FUT1 mutations associated with Bombay phenotype are present at elevated frequencies in particular communities, castes, or regional populations within South Asia, and if migration patterns preferentially select from those same populations, then the frequency of Bombay blood within British South Asian communities could be considerably higher than the average for South Asia as a whole. Migration does not take a random sample of a genetic population. It takes a biased sample, shaped by economics, politics, social networks, and historical contingency. And that bias has consequences that show up in blood banks decades later. The Gujarati connection is particularly significant and has been noted in transfusion medicine literature. Gujarat, on the western coast of India, is the home region of a large number of British South Asians, particularly those who came via East Africa. The Gujarati communities that settled in East Africa during the British colonial period, many of them brought over as labourers and merchants to support infrastructure projects like the Uganda Railway, maintained strong internal community ties and relatively endogamous marriage practices. They married predominantly within their own communities, within their own castes, which in Gujarati society are elaborate, complex, and deeply maintained social structures. Endogamy, marriage within a defined group, concentrates genetic variants. Rare mutations that would be diluted away in a large randomly mating population persist and can increase in frequency within endogamous communities. When Gujarati families arrived in Britain in significant numbers, particularly in cities like Leicester, which became home to one of the largest Gujarati communities outside India itself, they brought their marriage practices with them. Not universally, not without adaptation, but substantially. Arranged marriages, and particularly marriages within the same caste or community of origin, remained common enough across generations to maintain a degree of genetic continuity with South Asian population structures. And that means that Bombay blood, if present at elevated frequencies in particular Gujarati sub-communities, would tend to persist at those elevated frequencies in the British Gujarati diaspora rather than diluting toward the British population average. This is not a small consideration. It is, in fact, the central genetic mechanism by which Bombay blood became more concentrated in Britain than almost anywhere in the world outside of its South Asian places of origin. The combination of large-scale migration from populations with above-average Bombay blood frequencies, sustained by community structures that maintain genetic continuity across generations, explains what looks at first glance like a statistical anomaly. Britain is not an anomaly. Britain is the downstream consequence of history. But there is more to this story than migration from South Asia, because Britain itself is older than the empire, and the genetics of Britain, before any of this happened, already contain surprises that intersect with the story of Bombay blood in ways that nobody anticipated until relatively recently. To understand why, you have to understand something about the deep prehistory of Britain and about what the island's population actually looked like before Romans, before Saxons, before Normans, before any of the headline-grabbing invasions that dominate the school curriculum. Ancient DNA research has transformed how geneticists think about the British population. Studies conducted over the past 15 years, extracting and sequencing genetic material from the bones of people buried across Britain over thousands of years, have revealed a pattern of migrations and replacements far more dramatic than anyone predicted. The people who built Stonehenge, who farmed Neolithic Britain around 5,000 years ago, were themselves descended from earlier agricultural populations that had moved into Britain from continental Europe around 6,000 years ago, replacing or absorbing the Mesolithic hunter-gatherers who had occupied the island since the ice sheets retreated. Then around 4,000 years ago, a massive migration from the eastern steppes, the Bell Beaker phenomenon, swept across Britain and largely replaced the Neolithic farming population. The genetic turnover was enormous. Within a few centuries, the population of Britain was largely descended from these new arrivals, who were themselves related to the Yamnaya culture of the Pontic steppe. None of this directly connects to Bombay blood, but it establishes something important. The British population is not, and has never been, a static genetic entity. It is the result of multiple waves of migration, replacement, and mixture. And each wave brought its own set of genetic variants, including its own set of rare alleles, into the developing pool of British genetics. The specific mutations associated with Bombay phenotype were not, as far as current evidence shows, present in early British populations in meaningful frequencies. But the principle holds. Britain's genetic history is a history of movement, and the movement does not stop in the Bronze Age. Romans came. Romanized Britons mixed with soldiers drawn from across the empire, North Africa, the Levant, Syria, the Rhine frontier. Anglo-Saxons came from what is now northern Germany and Denmark, bringing their genetics into a post-Roman Britain. Vikings settled across northern and eastern England, in the Danelaw territories, along the Scottish coasts, across Ireland. Normans arrived in 1066 with their French and Norse and Frankish ancestry. Flemish weavers settled in medieval English towns. Sephardic Jews arrived after their expulsion from Spain in 1492. Huguenots came fleeing religious persecution in France. Each wave smaller than the last in terms of demographic impact, but none of them zero. Britain absorbed them all, not always gracefully, not always willingly, but genetically, yes, always. By the time the first South Asian Lascars were walking the streets of early modern London, they were entering a country that was already genetically complex, in ways that its inhabitants would not have recognized and would not have measured for another 4 centuries. And by the time large-scale South Asian migration began in earnest in the mid-20th century, the country they entered had itself been shaped by a millennium and a half of arrivals from every direction. The Bombay blood that those migrants carried entered not a monolithic genetic space, but a layered, shifting, historically accumulated one. The actual clinical discovery of Bombay blood in British patients came quietly, without fanfare, as most medical discoveries do. Transfusion medicine in mid-20th century Britain was still a relatively young field. The National Blood Transfusion Service had only been established in its modern form during the Second World War, when the scale of casualties made systematic blood collection and storage an urgent national priority. Before the war, transfusion had been a relatively ad hoc affair, conducted directly between donor and recipient, limited in scope, prone to catastrophic failures when typing was imprecise or incomplete. The wartime transfusion service built the infrastructure, the laboratories, the cold chain, the donor registration systems that would underpin British blood medicine for generations. But it built them around the knowledge that existed at the time. In 1940, the ABO system was well understood. The H factor had just been characterized by Landsteiner and Wiener, though its clinical implications were still being worked out. The hundreds of other antigen systems, including the H antigen system, were either unknown or poorly characterized. Transfusion medicine in 1945 was enormously more sophisticated than it had been in 1914, but it was still operating with fundamental blind spots. The discovery of Bombay blood by Bende in 1952 reached British transfusion scientists within a few years. The British blood typing establishment, centred on laboratories in London and Bristol and linked to the Medical Research Council's Blood Group Research Unit, was small, internationally connected, and genuinely, scientifically curious. When an anomaly appeared in India, British researchers paid attention. They began looking for similar cases in their own patient populations. They found them, not many at first, and mostly not in the general British population. They found them in the South Asian patients whose communities were growing in industrial British cities, in the families of migrants who had come through the 1950s and early 1960s. Each confirmed case of Bombay phenotype in a British patient created an immediate clinical problem. The patient could not receive standard blood. They could not receive blood type O, which is what emergency rooms reach for when they have no time for detailed typing. They could not receive any standard blood at all, and they could not donate to the general supply because their antibodies would render any blood they donated hazardous to H-positive recipients. They existed in a category outside the normal system, requiring a parallel network, a separate registry, a mechanism for locating compatible donors across distances that made no logistical sense for a blood emergency. The British approach to this problem developed slowly and somewhat imperfectly over the following decades. Reference laboratories, particularly the International Blood Group Reference Laboratory in Bristol, which was among the most sophisticated blood typing facilities in the world at the time, began maintaining records of unusual blood phenotypes, including Bombay. Donors were registered. Contact information was kept. When a patient presented with Bombay phenotype, the laboratory would search its records, contact potential donors, and coordinate whatever was possible. The system worked, when it worked, through networks of trust and rapid communication. A Bombay-type donor in Birmingham could potentially provide blood for a Bombay-type patient in Manchester or Cardiff or Glasgow. A Bombay donor in India, through the international connections maintained by bodies like the International Society of Blood Transfusion, could potentially be contacted for a patient in London if the urgency was sufficient and the logistics could be managed. The networks were fragile. They depended on current contact information for donors who might have moved, changed their phone numbers, died, or emigrated. They depended on laboratories, with the expertise to confirm typing quickly. They depended on freezing and transport infrastructure that could preserve autologous blood the patient themselves had pre-donated, which was the safest option of all, for people with rare phenotypes who had planned ahead. Planning ahead required knowing. And this was, and to some extent remains, the fundamental challenge of Bombay blood in Britain. The phenotype is rare enough that most affected individuals never know they have it until there is a crisis. A routine blood test does not identify Bombay phenotype. Standard ABO typing produces a result that looks like blood type O because the cells have no A or B antigens. Only specialized testing, specifically testing for the presence of H antigen and anti-H antibodies, reveals the true situation. And that testing is not routine. It is done when something goes wrong, when a cross-match fails, when a patient has an unexpected transfusion reaction, when a physician orders extended typing because a routine transfusion produces the wrong result. This means that most of the Bombay-type individuals living in Britain today do not know they are Bombay-type. They live ordinary lives, go to ordinary general practitioners, have ordinary blood tests for ordinary reasons, and receive ordinary results. The potential emergency is invisible until it is not, and when it becomes visible, it tends to become visible in the worst possible way, in a hospital, in crisis, with limited time. The demographics of Bombay blood in Britain mean that the communities most affected are also, historically, communities that have faced significant barriers to healthcare engagement. South Asian communities in mid-20th century Britain encountered healthcare systems that were sometimes indifferent, sometimes actively hostile, often culturally and linguistically inaccessible. The National Health Service was a remarkable achievement of the post-war settlement, but its initial design was built around assumptions about the population it would serve, assumptions that did not fully account for the medical needs of the new communities arriving in industrial Britain in the 1950s and 1960s. Extended blood typing was not a priority in busy urban practices. The specific risks of Bombay blood were not widely known among general practitioners, even if they were understood by specialists in transfusion medicine. The gap between what specialists knew and what frontline clinicians knew about Bombay blood persisted for decades. Even in the 1980s and 1990s, there were documented cases of near-catastrophic outcomes when Bombay patients received standard blood in emergencies because their unusual phenotype had not been identified. The problem was not ignorance in the absolute sense. It was the way medical knowledge moves through a system, from reference laboratories and specialist journals to busy emergency departments and general practice surgeries, a process that can take decades and is never complete. The situation began to change meaningfully with improvements in computing and database management in the late 1980s and through the 1990s. NHS Blood and Transplant, the body that now manages England's blood supply, developed increasingly sophisticated databases for rare blood donors. The National Rare Donor Programme, though not exclusively focused on Bombay blood, created better mechanisms for locating compatible donors across the country when rare phenotype patients were identified. International collaboration improved. Links between British transfusion services and Indian blood banks became more formalised as the South Asian diaspora in Britain grew and as awareness of Bombay blood among South Asian communities increased. Community-based awareness campaigns, run partly through South Asian community organisations and partly through NHS outreach programmes, began reaching people who might be Bombay type but did not know it. These campaigns were culturally specific, linguistically accessible, and built on the trust that community organisations had developed with populations that had reason to be cautious about institutional medicine. They were not uniformly successful. They did not reach everyone, but they registered a measurable number of new Bombay donors and identified Bombay phenotype individuals who could be counseled about their medical situation and encouraged to pre-donate autologous blood. The emergence of molecular genetics transformed Bombay blood testing from a purely serological exercise to a genotypic one. Instead of just testing for the presence or absence of antigens on cell surfaces, laboratories could now sequence the FUT1 gene directly, identifying the specific mutation or mutations responsible for the phenotype. This mattered because different mutations have different implications. The most common FUT1 mutations in South Asian populations include several specific point mutations and deletions that are well characterized. Knowing which mutation a patient carries allows for more precise family screening, since first-degree relatives of Bombay-type individuals have a significantly elevated probability of carrying the same mutations and should be tested. Family screening is where the British situation becomes particularly interesting from a population genetics perspective. If Bombay phenotype is present at elevated frequencies in certain endogamous communities, and if those communities tend toward marriage within the community, then affected individuals are likely to have relatives who are also affected or who are carriers for the relevant mutations. The concept of a carrier for Bombay blood is somewhat different from carrier status for a recessive condition like cystic fibrosis, but the principle of concentration within family networks applies. A Bombay-type person in Leicester is more likely to have Bombay-type or Bombay mutation carrier relatives in Leicester, in Birmingham, in Nairobi, in Ahmedabad, than a randomly selected member of the British public. The networks are real, genetically as well as socially. This network structure is both a vulnerability and a resource. Vulnerability, because it means Bombay blood concentrations tend to cluster in ways that constrain local blood bank resources when multiple affected individuals need care simultaneously. Resource, because it means that community-based donor recruitment, targeting the right social networks, can be disproportionately effective at identifying compatible donors. A single well-connected Bombay-type donor who actively recruits within their community can lead to the identification of multiple other donors. The social capital of close-knit communities, which has sometimes been mischaracterized in broader public debates about South Asian integration, is in this context a genuine medical asset. The genetics of Bombay blood in the British context also intersect with a question that researchers in human population genetics have been examining with growing interest. What can rare blood phenotypes tell us about population structure, migration history, and the degree of genetic continuity or discontinuity within diasporic communities? Bombay blood, precisely because it is rare and because its molecular basis is well characterized, serves as a kind of genetic marker, a way of tracing the persistence of specific ancestral populations within the broader British genetic landscape. Studies examining the frequency of Bombay blood within British South Asian communities have found, as one might expect given the migration history described above, that frequencies vary significantly across different community groups. British Gujarati communities show higher frequencies than British communities with origins in Mirpur or Sylhet, because the underlying population frequencies are different in those regions of origin. British Punjabi communities fall somewhere in between, reflecting different South Asian baseline frequencies. These differences are not absolute, because communities do intermarry, do mix, do change across generations, but they persist at a detectable level, reflecting the fact that migration patterns brought specific regional genetic signatures into specific British communities, and those communities have maintained enough internal cohesion to preserve some of that regional signal. This is not unique to South Asian communities in Britain. The same principle applies to any diasporic population that maintains a degree of endogamy. Irish communities in Britain show elevated frequencies of certain alleles common in Ireland. Caribbean communities show genetic signatures that trace to specific West African regions. Jewish communities, with a long history of endogamy across many countries, show elevated frequencies of certain variants, including some with medical implications, like Tay-Sachs disease and BRCA mutations in Ashkenazi lineages. The persistence of genetic structure within diaspora communities is not a function of clannishness or failure to integrate in some social sense. It is a function of marriage patterns and marriage patterns are among the most slowly changing aspects of any culture. They change, but they change across generations, not within them. The implication for Bombay blood is that British South Asian communities, particularly those with Gujarati ancestry, will continue to show above-average frequencies of Bombay phenotype for the foreseeable future, even as intermarriage rates gradually increase and genetic mixing slowly dilutes the signal. The transition from high-frequency endogamous communities to lower-frequency mixed communities takes many generations, and even then does not reach zero. The rare alleles persist in the population, carried by individuals who may be wholly integrated in every social sense, but who still carry the genetic signature of their ancestors' specific origins. Blood does not forget where it came from, even when everything else does. There is something about this that deserves more than clinical commentary. The story of Bombay blood in Britain is, at one level, a story about a medical anomaly, a rare blood type that creates dangerous situations and requires elaborate workarounds. But, at another level, it is a story about what happens when human movement, driven by empire and economics and politics and the simple human desire for a better life, writes itself into the biology of a receiving population. The South Asian communities that brought Bombay blood to Britain did not bring it as a problem. They brought it as part of themselves, as part of the genetic heritage of populations that had been living and reproducing and moving and mixing on the Indian subcontinent for thousands of years before a single British ship ever rounded the Cape of Good Hope. The British blood bank system's engagement with Bombay blood is, in this reading, a story about institutions learning to account for the biological diversity that human movement creates. Not just the cultural diversity that dominates public discourse about migration, the food, the language, the religious practice, the social customs, but the biological diversity, the variations in drug metabolism, the variations in disease susceptibility, the variations in surgical and transfusion risk, the variations in genetic carrier status. All the ways in which the human body, shaped by thousands of years of population-specific selective pressures, carries its history into new environments and requires healthcare systems to update their assumptions. This is not a simple lesson, and it is not a cheap one. The NHS has invested real resources in understanding and managing Bombay blood and other rare phenotypes. The science is genuinely difficult. The logistics are genuinely complex. The community outreach required to identify affected individuals before a crisis occurs is expensive and time-consuming. But the alternative, a healthcare system that treats rare blood phenotypes as someone else's problem until the emergency is already happening, costs more in the end. In lives, not just money. To understand where Bombay blood fits in the larger story of human blood diversity, you have to go back much further than the East India Company, much further than the first South Asian sailors in Tudor London, much further than the Roman Empire or the Bronze Age steppe migrations. You have to go back to Africa, 60,000 or more years ago, to the populations that would eventually leave and spread across every habitable part of the planet, carrying their genetic diversity with them into environments and conditions and selective pressures that their ancestors had never experienced. Human blood diversity is one of the most striking examples of what evolutionary biologists call balancing selection, the process by which natural selection maintains multiple variants in a population rather than driving one to fixation. The ABO blood type system is perhaps the most famous example. All three major alleles, the A allele, the B allele, and the O allele, which is actually a loss-of-function mutation in the A allele, have been present in human populations for hundreds of thousands of years. None has been eliminated. None dominates completely. The reason is almost certainly that different blood types offer different resistances and susceptibilities to different pathogens, and the optimal balance shifts depending on which pathogens are prevalent in a particular environment. A blood type is more common in populations that were historically exposed to plague. O blood type is more common in populations that were historically exposed to certain strains of cholera. B blood type has its own epidemiological correlates. The variation is maintained because the environment of pathogens is never uniform and never stable. The H antigen system, the system that Bombay blood disrupts, sits in a different relationship to selection than the ABO system. The H antigen is not just a blood group antigen. It is a surface molecule present on many cell types beyond red blood cells. It appears in secretions. It interacts with pathogens in complex ways. Some bacteria, including certain strains of Helicobacter pylori, the organism responsible for most stomach ulcers, use H antigen and related molecules as attachment points. People who are non-secretors, who do not produce H antigen in their secretions due to FUT2 mutations, are thought to be protected against certain H. pylori strains because those strains cannot attach as effectively to their gut lining. This is the kind of pathogen-mediated selection that could plausibly maintain elevated frequencies of H-related mutations in populations with high H. pylori exposure. But Bombay blood, the complete absence of H antigen, is different from non-secretor status. It is more extreme, and the selection dynamics are correspondingly more complex. The complete absence of H antigen means the individual's immune system has developed anti-H antibodies, treating H antigen as foreign. This creates the transfusion problem that defines Bombay blood clinically. But, from a pathogen interaction perspective, it might mean that organisms that use H antigen as an attachment point simply cannot attach at all. If any pathogen relied heavily on H antigen for infection, Bombay-type individuals would be essentially immune to that route of infection. That is a potentially significant fitness advantage in an environment where that pathogen was prevalent. Whether this mechanism actually explains the elevated frequencies of FUT1 mutations in South Asian populations is unknown. It remains in the realm of hypothesis. But it is a plausible hypothesis, and it matters because it reframes Bombay blood from a pure medical anomaly into something more interesting. A possible evolutionary response to a specific disease environment. A biological adaptation, or the byproduct of one, that has persisted because the selective environment that favored it, a world of specific infectious threats, persisted long enough to drive the mutation to frequencies higher than pure drift would predict. The deep human population genetics behind Bombay blood also connects to debates about the origin of South Asian populations that have been transformed by ancient DNA research over the past decade. The Indian subcontinent was colonized by anatomically modern humans in one of the earliest out-of-Africa dispersals, probably more than 60,000 years ago. Those initial colonizers, sometimes called the ancient ancestral South Indians, were the foundation population from which much of South Asia's diversity eventually derived, but they were not the last arrivals. Around 4,000 to 5,000 years ago, a second major wave of migration brought populations related to the early European farmers, people who had themselves been part of the Neolithic agricultural expansion from the Middle East and Anatolia into the subcontinent from the northwest, and roughly contemporaneously, populations from the Eurasian steppe related to the same Yamnaya expansion that so dramatically reshaped Europe also entered South Asia, eventually giving rise to the ancestors of many upper-caste North Indian populations. The result of these migrations is that modern South Asian genetic diversity is extraordinarily complex, a layered mixture of the three major contributing ancestries in varying proportions across different castes, regions, and communities. The ancient ancestral South Indian component is highest in the south and in lower caste populations that were historically less connected to the migration routes from the northwest. The ancestral North Indian component, which reflects both the early European farmer ancestry and the steppe ancestry, is higher in the north and in upper caste populations. And, within this complexity, specific genetic variants, including the FUT1 mutations associated with Bombay blood, are distributed in patterns that reflect both the underlying population structure and the specific demographic history of the communities where they are elevated. This means that asking where Bombay blood comes from is actually asking about specific lineages within South Asian genetic history, lineages that can be traced using modern genomic tools to specific ancestral population contributions. The mutations are not uniformly distributed across all South Asian populations. They cluster, they concentrate, and their clustering reflects the particular histories of the communities where they appear, histories of geographic isolation, of caste endogamy, of founder effects, of demographic contractions and expansions across centuries. The caste system deserves specific consideration here because it is one of the most powerful mechanisms of genetic isolation ever documented in human history. Indian castes have practiced endogamy, marriage within the caste group, for at minimum 2,000 years and possibly longer. The genetic consequences are extraordinary. Studies using modern genomic sequencing have shown that many Indian castes have effective population sizes, meaning the number of genetically distinct ancestors their current populations trace to, that are extraordinarily small. Some upper castes in South India appear to trace their entire current population to a few dozen ancestors who lived 2,000 to 3,000 years ago. The genetic diversity within these castes is lower than would be expected in a randomly mating population many times their size. And rare variants that would be diluted away by admixture in an outbred population, persist and even rise in frequency within these endogamous groups. This is the mechanism by which Bombay blood, or any rare genetic variant, can become elevated in a specific community within South Asia. The community is not genetically large. It does not intermarry freely with other communities. Over many generations, whatever variants were present in the founding population, including rare variants like specific FUT1 mutations, become characteristic of the community, part of its genetic signature, in a way that would not happen in a freely mixing population. When members of that community migrate to Britain, they carry that signature with them. And when their descendants maintain community endogamy in Britain, however partially and imperfectly, they maintain the signature across generations. The British caste dynamics are not identical to Indian ones. The social pressures are different. The policing mechanisms are different. The degree of external mixing is higher, but the principle operates even in attenuated form. British South Asian communities have maintained significantly higher rates of within-community marriage than the British population as a whole, particularly in the first and second generations after migration. This is documented in demographic surveys and is not controversial among researchers who study South Asian diaspora communities. The rates vary by community and region and generation, but the tendency exists and has genetic consequences. There is also another dimension to this story that gets almost no attention in standard discussions of Bombay blood, which is the question of what the British healthcare system's encounter with Bombay blood has revealed about its own assumptions and limitations, and what those revelations have driven in terms of institutional change. The NHS is, by global standards, a remarkably inclusive and comprehensive healthcare system. Its founding principle, that healthcare should be free at the point of need for everyone, regardless of ability to pay, is genuinely radical and genuinely important. But inclusion in principle does not always translate into inclusion in practice, particularly when the medical knowledge base itself was built around assumptions that excluded certain populations. Bombay blood forced British transfusion medicine to reckon with the limits of its existing framework in a very concrete way. The discovery that a significant number of patients in British hospitals carried a blood type that the standard system could not accommodate, that could not receive standard emergency blood without risk of death, was not a comfortable discovery. It required the system to extend its technical capabilities, to establish new registries, to develop new protocols, to invest in community outreach in ways that the standard blood service model had not previously required. It required, in short, that the institution change to accommodate the biological diversity of the population it served, rather than requiring that the population conform to the institution's existing categories. This is a pattern that recurs throughout the history of medicine's engagement with diverse populations. Every expansion of a healthcare system's patient base, whether through geographic expansion, demographic change, or simply better recognition of previously ignored groups, reveals new biological complexities that the existing framework did not account for. The medical establishment's response to these revelations has not always been graceful. History is full of examples of medical institutions pathologizing difference, treating the biological characteristics of minority populations as aberrations, requiring correction rather than variations requiring accommodation. The story of Bombay blood in Britain is not that story. It is, more charitably, the story of a system slowly and imperfectly updating itself to reflect a demographic reality that its founders did not anticipate. The British response to Bombay blood also connects to a broader debate within transfusion medicine and hematology about the need for greater diversity in blood donor registries. The problem is not unique to Bombay blood. It applies to many rare blood phenotypes that are more common in specific ethnic communities than in the general population. The Rh system, which includes not just the standard D antigen, but dozens of other antigens, produces rare phenotypes that cluster in populations of African descent. The Duffy antigen system, which is nearly absent in populations of West African origin, has implications for malaria susceptibility and for transfusion compatibility in patients of African ancestry. The KEL system contains rare phenotypes that are clinically significant. All of these are cases where a blood supply drawn predominantly from donors of Northern European ancestry is poorly suited to serve the needs of patients from other genetic backgrounds. The problem has been recognized for decades, but progress in addressing it has been slow. Recruiting blood donors from underrepresented communities requires sustained effort, cultural competence, community trust, and resources that are not always available. The COVID-19 pandemic, which disproportionately affected certain minority communities and also disrupted established blood donation patterns, brought this issue into sharper focus in Britain, as NHS Blood and Transplant launched renewed efforts to recruit Black, Asian, and mixed heritage donors. Bombay blood is the extreme end of this spectrum, a phenotype so rare that even ambitious donor recruitment programs from South Asian communities can only add small numbers of confirmed Bombay donors to the registry. But the extreme case illuminates the general principle. A healthcare system that serves a diverse population must have a blood supply that reflects that diversity, and building such a blood supply requires understanding the genetics of that diversity at a level of detail that goes far beyond standard ABO and Rh typing. The science of blood typing is, in this sense, always catching up to the science of human population genetics. Genomic research has identified hundreds of blood group antigens and thousands of allelic variants within the known blood group systems. Only a small fraction of these are clinically relevant in standard transfusion practice. But for specific patients with specific medical histories, with previous transfusions, with alloimmunization, with rare phenotypes like Bombay, the relevant fraction is larger. And for those patients, the gap between what the blood supply can provide and what they safely need can be a matter of life and death. The future of rare blood management in Britain, as in most developed healthcare systems, lies in three developments that are already underway. The first is extended molecular typing of blood donors, moving beyond basic ABO and Rh serology to genomic characterization of donors' full blood group antigen profiles. This creates a much richer database of what any given unit of blood actually contains at the molecular level, allowing much more precise matching for patients with complex needs. The second is the development of stored autologous blood programs, specifically for rare phenotype individuals, encouraging people with Bombay or other rare phenotypes to donate blood for their own future use and to maintain a frozen stock that can be retrieved in emergency. The third is the development of artificial blood products, synthetic oxygen carriers, or laboratory-grown red blood cells that could be engineered to lack all H antigen and thus be compatible with Bombay-type recipients. All three of these are making progress. None of them are fully realized yet. Molecular blood group typing is becoming standard in many reference laboratories, but is not yet routine in all clinical settings. Autologous donation programs exist, but reach only the small fraction of Bombay individuals who have been identified and counseled. Artificial blood research has advanced significantly since the early attempts at hemoglobin-based oxygen carriers in the 1980s and 1990s, but fully viable synthetic red blood cells remain a research project rather than a clinical reality. The gap between the need and the available solutions remains real, and it is felt most acutely by the communities most likely to carry rare phenotypes like Bombay blood. There is a dimension to the Bombay blood story that transfusion medicine literature tends to treat as peripheral, but which is in fact central to how most people in affected communities actually experience this condition. It is not the science, it is the human story. The moment when someone finds out, the way the information moves through a family, the decisions that get made, or not made, in the aftermath. Consider what it means to discover, as an adult, that you have a blood type outside the standard system. Not a blood type that is rare and manageable in the usual sense, not being AB negative or a rare Rh type, where compatible donors are hard to find but not impossible, but a blood type that places you outside the grid entirely. A blood type where a mistaken transfusion could kill you faster than the condition that required the transfusion. A blood type where the only people who can safely help you are strangers you will never meet, connected to you not by kinship or community or shared history, but purely by the biology of a single gene on chromosome 19. The discovery usually comes without warning. A person goes to hospital for something unrelated, a surgery, a childbirth complication, an accident. Routine blood typing is done. The technician notices something wrong with the crossmatch. Further testing is ordered. And then someone sits down with the patient and explains that they have a blood type called H-null phenotype, or Bombay blood, and that this means the following things about their future care, and that the following people need to be contacted, and that the following steps are strongly recommended. The reaction to this information varies enormously. Some people absorb it practically, immediately focused on logistics. Who needs to know? What cards to carry? What to tell surgeons? Others are frightened in ways that take time to fully process. The information carries a weight that is difficult to communicate to someone who has never received it. It is not exactly a death sentence, because modern transfusion medicine provides real safeguards, but it is a permanent modification of how you must think about your own body in relation to medical systems. Every surgery becomes more complicated. Every potential accident carries an additional layer of risk. Every hospital visit requires a conversation about your blood type that most people never have to have. For British South Asian individuals who receive this diagnosis, the experience is often compounded by the need to communicate across family networks that may span multiple countries. The genetics of Bombay blood are such that immediate family members have elevated probability of carrying the same mutations. Brothers, sisters, parents, children should all be tested. In a family whose members are distributed between Birmingham and Gujarat, between Leicester and Mumbai, between Manchester and East Africa, coordinating this testing requires navigating different healthcare systems, different cultural attitudes toward genetic information, and different levels of understanding of what Bombay blood means and why it matters. Within British South Asian communities, the concept of a genetic condition that concentrates within families and within community groups carries social implications that mainstream healthcare providers do not always fully appreciate. In communities where marriage is arranged within the community, and where genetic conditions carry social stigma, the revelation that a genetic variant associated with a medical condition is present in a family can affect marriage prospects, can influence how information is shared or withheld, can create pressures that are invisible to clinicians focused purely on the medical management of the condition. This does not mean that affected individuals and families handle the information irrationally. It means they are navigating a complex social context simultaneously with navigating a complex medical one, and that healthcare providers who are unaware of that social context will often misread the family's responses. Cultural competence in the management of Bombay blood is not about making assumptions about any South Asian family's specific values or practices. It is about understanding that medical information never exists in a social vacuum, that the way information is received and acted upon is shaped by context, and that providers who engage with that context will produce better outcomes than those who deliver information and walk away. This is true for any patient with complex medical needs, but it is particularly acute for conditions that concentrate in specific communities and that carry familial implications. The transfusion medicine community in Britain has become increasingly aware of this over the past 2 decades. Programs linking hospital hematology services with community health workers and with South Asian community organizations have improved the rate at which Bombay-type individuals and their relatives are identified, counseled, and enrolled in autologous donation programs. The improvement has not been uniform across the country. In cities with large, well-established South Asian communities and strong links between community organizations and NHS services, the networks work reasonably well. In areas with smaller or more dispersed South Asian populations, the networks are thinner, the awareness lower, and the risk of an unidentified Bombay patient presenting in emergency is correspondingly higher. There are also real limitations in how British law and medical ethics handle genetic information in the context of family screening. The GDPR framework that governs data protection in the United Kingdom creates constraints on how medical information about one family member can be shared with others without explicit consent. A hospital that identifies a Bombay-type patient cannot simply contact that patient's relatives to recommend testing without the patient's agreement and active cooperation. This is appropriate from a privacy standpoint, but it creates genuine challenges in conditions where family-wide screening is medically important. The ethics of how to communicate genetic risk within families, balancing individual privacy against collective family interest, is a live debate in clinical genetics that has no simple answers. Some of the most striking stories from British Bombay blood cases involve the way the condition crosses generations and geographies in unexpected ways. A woman in Leicester, British-born, whose parents came from Gujarat in the early 1970s, discovers she is Bombay type during a routine pre-operative workup. She contacts her siblings. Two of her brothers are also Bombay type. Her parents are tested. Both are carriers, but are themselves phenotypically normal because they are heterozygous, carrying one copy of the FUT, one mutation, but one functional copy as well. A Bombay phenotype requires two mutated copies. Her parents never knew. Her grandparents almost certainly never knew. The mutation was there in the family's genetic history for generations before there was any medical system capable of identifying it, let alone managing its consequences. This multi-generational invisibility is characteristic of recessive conditions, but it has a particular poignancy in the case of Bombay blood because the condition's implications were entirely without consequence until the era of modern transfusion medicine. Before blood typing, before blood transfusion, Bombay-type individuals lived and died without their unusual blood type ever mattering to their health in any specific way. The mutation was invisible because the technology to make it visible did not exist. It only becomes a condition at all in the context of modern medicine, because modern medicine created the practice of transfusion, which created the possibility of incompatible transfusion, which created the risk that Bombay blood now represents. This is an unusual feature of Bombay blood that distinguishes it from most genetic conditions. A person with sickle cell disease suffers from their condition in all historical periods, regardless of medical context. A person with Huntington's disease develops neurological deterioration, regardless of whether a neurologist ever diagnoses them. But a Bombay-type person in a world without blood transfusion has no medical condition associated with their blood type at all. They are simply a person. Their blood flows, carries oxygen, clots normally at wounds. Nothing about their experience of their own body reveals the unusual molecular architecture of their red cell surfaces. The condition is entirely an artifact of the medical context in which it appears. This means that the history of Bombay blood as a medical concern is very short. It begins in 1952 and extends forward from there. But the genetics of Bombay blood are old. The FUT1 mutations that produce it have been present in human populations for a long time, though molecular clock estimates for specific mutations are uncertain. They are old enough to have been present in the founding populations of the communities where they are now elevated, old enough to have been distributed across the world as those communities migrated, old enough to be deeply embedded in the genetic heritage of the British South Asian diaspora. The intersection of old genetics and new medicine is where the strangeness of Bombay blood is most concentrated. You have a biological variant shaped by evolutionary forces operating across millennia, distributed across populations by migration patterns spanning centuries, concentrated in communities by social practices, including the caste system, with histories stretching across thousands of years. And you have a medical technology, blood transfusion, that is less than a century old in its effective modern form, that has created the context in which this ancient biological variant suddenly becomes visible, suddenly becomes a medical problem, suddenly becomes the subject of registries and protocols and community outreach campaigns. These two timescales, the evolutionary and the medical, do not fit comfortably together. The evolutionary history of Bombay blood is a story measured in generations, in demographic expansions and contractions, in the slow accumulation of genetic drift, in the long interaction between human populations and their pathogen environments. The medical history of Bombay blood is a story measured in decades, in the development of blood banking infrastructure, in the growth of South Asian communities in Britain, in the gradual accumulation of clinical knowledge and institutional response. Neither story makes complete sense without the other, and the challenge of managing Bombay blood in a modern healthcare system is essentially the challenge of aligning these two very different timescales, of making a medical system responsive to evolutionary history, of allowing ancient genetics to shape modern institutional practice. To those working in British transfusion medicine, This is not an abstract philosophical observation. It is a daily, operational reality. The rare donor coordinators, who maintain the Bombay phenotype registry, who call donors when a patient needs blood, who negotiate the logistics of frozen autologous stock, are working at the intersection of population genetics and clinical emergency medicine. They need to understand both. They need to know why Bombay blood is more common in certain communities, which requires population genetics. And they need to know how to respond when a Bombay patient presents in emergency, which requires clinical protocols. The gap between those two kinds of knowledge and the institutional barriers that separate the scientists who understand the genetics from the clinicians who manage the emergencies is one of the structural problems that the British healthcare system has been slowly and imperfectly addressing for decades. There is also a larger story here about how medicine understands and responds to human genetic diversity more broadly. The history of medicine in the 20th century was, for most of its course, a history of seeking universal treatments, universal protocols, universal biological frameworks that could be applied to all patients regardless of their specific genetic background. This universalism was valuable. It produced the antibiotic revolution, the vaccine revolution, the surgical revolution. It saved hundreds of millions of lives, but it was also, inevitably, a universalism built on assumptions about what counted as the universal human baseline. In practice, the baseline was often the adult male of Northern European descent, the subject most commonly studied in clinical trials through most of the 20th century, the patient whose physiology was most familiar to institutions built in Northern European countries. This is not a conspiratorial observation. It is a documented feature of how medical research was historically organized, and its consequences are visible in everything from dosing recommendations that were calibrated on male bodies to diagnostic criteria developed on populations that excluded certain groups. Bombay blood sits at an extreme end of what happens when that universal baseline fails to account for the actual biological diversity of the human population. It is a case where the failure is acute and the consequences are potentially fatal. The medical community's response to Bombay blood has been, by and large, an appropriate and genuinely responsive one. The condition was documented relatively quickly after it was first identified. The clinical implications were recognized and acted upon. Registries were established, protocols were developed, community outreach was attempted and improved over time. The fact that the system has not been perfect, that individuals have been missed, that emergencies have sometimes unfolded without adequate preparation, is a function of resource constraints and institutional inertia rather than indifference. But the lesson of Bombay blood is broader than the management of a single rare phenotype. It is a lesson about the cost of building medical systems that assume biological uniformity in a world characterized by biological diversity. Every population that has been poorly represented in blood donor registries, in clinical trials, in medical research generally, represents a potential repository of biological variation that the medical system does not yet fully understand or adequately serve. Bombay blood is the case study. The principle extends much further. There is a question that emerges naturally from the story of Bombay blood in Britain, and it is not a comfortable question, but it is an honest one. When we talk about the genetic consequences of migration, about rare blood types carried by specific communities, about the way that population structure shapes medical risk, we are walking close to territory that has historically been exploited for very different purposes. The relationship between genetics, population, and identity has a dark history, one that responsible researchers must always keep in view, even when the specific content of what they are discussing is entirely benign. The story of Bombay blood is not a story about one community being genetically inferior or genetically superior to another. It is not a story about the dangers of mixing or the virtues of separation. It is a story about how human populations have moved through time, how genetic variants have been distributed by history rather than by any essential difference between people, and how a healthcare system must respond when that distribution creates specific clinical challenges. The genetics here are morally neutral. The migration history behind them is complex and often painful, shaped by empire and economic inequality and the human need for safety and opportunity. But the genetics themselves carry no value judgment. This is worth stating explicitly because discussions of rare genetic variants in specific ethnic communities are sometimes weaponized by people who wish to make entirely different arguments. The concentration of Bombay blood in British South Asian communities does not imply anything about the relative fitness or health or value of those communities. It implies something about migration history and population structure, which are historical and demographic facts, not evaluations. Bombay blood is not more or less noble in South Asian veins than in European or Japanese ones. It is simply more frequent in South Asian veins for reasons that are historical and statistical, not essential. The researchers who study these questions are, by and large, acutely aware of this context and are careful about how they communicate their findings. The field of medical genetics has spent decades working through the implications of doing population-level genetic research, and while it has not always succeeded in avoiding harm, the dominant contemporary approach is one that treats population genetic variation as a product of history, migration, and chance, rather than as a reflection of any hierarchy of human worth. Keeping this in mind, let us return to the specific British context, and to what makes Britain's situation with Bombay blood genuinely unusual from a global perspective. The numbers matter here. Globally, the H0 phenotype is estimated to appear in roughly 1 in a million individuals in most populations. In parts of South Asia, particularly in certain communities in Maharashtra and Gujarat and other regions with elevated FUT1 mutation frequencies, the rate is significantly higher, perhaps 1 in 10,000, or even more in specific subpopulations. Britain, with a South Asian population of approximately 4 million people, and with that population disproportionately drawn from communities with above-average Bombay blood frequencies, represents a significant concentration of Bombay phenotype individuals in a country that otherwise would have almost none. If the South Asian component of the British population shows Bombay blood frequencies even half as high as the elevated South Asian averages, the total number of Bombay-type individuals in Britain could be in the hundreds. That sounds small in absolute terms, but against a global background rate of 1 in a million, it is enormous. Britain would have more confirmed and probable Bombay phenotype individuals than all of North America, all of Australia, all of continental Europe combined. The only places with more are India and Pakistan, and the other South Asian countries where the mutations arose, and where the populations are orders of magnitude larger. NHS Blood and Transplant maintains the most comprehensive rare blood phenotype registry in the United Kingdom, and through its links to the International Rare Donor Programme coordinates with rare blood registries in other countries. The organisation does not publish detailed numbers by phenotype and community for obvious privacy reasons, but the general picture is consistent with what population genetics would predict. A significant number of registered Bombay-type donors in Britain are of South Asian heritage, predominantly from communities with Gujarati or other Western Indian ancestry. The registry represents a small fraction of the actual Bombay-type population, because identifying Bombay individuals requires either clinical encounter and extended typing or active community screening programs that have not reached everyone. The practical implications of this concentration are felt most acutely in the cities where British South Asian communities are largest: Birmingham, Leicester, Bradford, Manchester, and the London boroughs with large South Asian populations. Hospital transfusion services in these cities see more rare phenotype cases than services in comparable cities with smaller South Asian populations. They have, correspondingly, developed greater expertise in managing these cases. The hematology teams in Birmingham's major hospitals, for example, have extensive experience with Bombay blood and other rare phenotypes that reflects their city's demographic reality. This expertise is valuable, but it is not uniformly distributed across the country, and a Bombay-type patient who presents in emergency at a smaller hospital in a less diverse area may face a longer and more uncertain path to appropriate care. The regional dimension of Bombay blood management in Britain connects to broader debates about how the NHS distributes specialist expertise and how it ensures that rare but serious conditions can be appropriately managed regardless of where a patient happens to be when they need care. Regionalisation of specialist services has been a persistent theme in NHS reform discussions, with the argument that concentrating expertise improves outcomes, but the counter-argument that geography creates barriers to access. Rare blood phenotypes are exactly the kind of condition where both arguments apply. Centralizing Bombay blood management expertise makes sense in one way. Ensuring that every hospital in the country can identify and immediately stabilize a Bombay patient before transfer to a specialist center is equally essential. The communication infrastructure that supports this has improved significantly with the digitization of medical records and the development of alert systems within hospital information technology. A patient with Bombay phenotype who has been previously identified can now, in principle, have their blood type flagged in electronic health records in a way that will immediately alert the clinical team when they present anywhere in NHS England. In practice, this works well for patients who are registered with the system, who have had previous clinical encounters that identified their phenotype, and whose records are properly maintained and accessible. It is less reliable for patients who have never been typed, who have moved across regional boundaries, or whose records are incomplete for any of the many reasons medical records can be incomplete. There is also an international dimension to the British Bombay blood story that deserves attention. The British South Asian diaspora is itself globally distributed. British citizens of South Asian heritage travel to India and Pakistan and East Africa and North America in large numbers for family visits, for business, for education. When a Bombay-type British citizen requires emergency care abroad, the system of rare blood management that protects them in Birmingham or Leicester may not extend to Mumbai or Nairobi or Toronto. International coordination is improving but is far from seamless. A British Bombay patient who is injured in an accident in rural India faces a situation where the local hospital may have excellent general capabilities but may never have encountered a Bombay phenotype case and may not immediately recognize that standard blood would be dangerous. The practice of Bombay-type individuals carrying information cards, identifying their blood type, and providing emergency contact information for relevant registries is recommended but not universally followed. Medical alert bracelets or cards specifying rare blood phenotypes are common in countries with established rare blood management programs, but uptake is variable. The behavioral challenge is real. Carrying a medical alert card requires a level of integration of medical identity into daily life that many people resist, particularly when their condition is invisible and they feel completely well. The resistance is human and understandable. The consequences of that resistance in an emergency are potentially severe. Community education campaigns in British South Asian communities have increasingly addressed this behavioral dimension. Working with community health workers and with organizations trusted by those communities, health educators have tried to communicate not just the fact of Bombay blood, but the specific practices that Bombay-type individuals should adopt to protect themselves. Pre-donating and freezing autologous blood, carrying identification of blood type, informing family members who should be tested, notifying any surgeon or anesthesiologist before elective procedures. These are practical steps that significantly improve outcomes, but they require that affected individuals know they are affected, understand what the condition means, and trust the healthcare system enough to engage with these practices. Trust is not a given. The history of South Asian communities in Britain includes significant experiences of institutional indifference, cultural insensitivity, and outright racism in healthcare settings, particularly in earlier decades. The degree to which those experiences affect current healthcare engagement varies across generations and communities, but they cannot be ignored. A community that has learned to navigate a healthcare system with caution, that has had relatives dismissed or misdiagnosed or treated as less important than other patients, will engage with messages from that healthcare system differently than a community with uniformly positive healthcare experiences. Building the trust that allows Bombay blood education to be effective requires acknowledging this history, not erasing it. The most effective healthcare programs addressing rare blood phenotypes in South Asian British communities have been those that start from this acknowledgement. They have worked through community organizations rather than imposing institutional frameworks. They have employed health educators from within the communities they serve, people who share language, cultural context, and lived experience with the individuals they are trying to reach. They have been patient, building trust over time, rather than expecting immediate compliance with recommended practices. And they have produced measurable results, not dramatic ones, but real ones, in the form of more identified Bombay donors, more pre-deposited autologous blood, more family screening, and fewer emergency situations unfolding without any preparation. The model that has worked best for Bombay blood management in Britain is, in a sense, the model that works best for any complex healthcare challenge in diverse communities. It is not a top-down model where the institution defines the problem and imposes the solution. It is a collaborative model where the institution brings technical expertise and resources, and the community brings trust networks, cultural knowledge, and the capacity for self-organization that comes from communities that have had to rely on internal networks because external institutions were unavailable or unresponsive. This collaborative model is not cheap or fast. It requires sustained investment in community partnerships. It requires institutional humility. It requires the patience to build relationships across cultural and historical divides that do not disappear because a well-meaning health policy is announced. But it is the only model that actually works for something like Bombay blood, where the affected population is small, defined by community membership as much as by genetics, and distributed across a country in ways that do not align neatly with standard healthcare catchment areas. Looking forward, the trajectory of Bombay blood management in Britain points towards several developments that are either underway or foreseeable. Genomic newborn screening, which is already being piloted in Britain for other conditions, could potentially be extended to include FUT1 genotyping, identifying Bombay phenotype individuals at birth, and ensuring that their status is known and recorded from the earliest possible point. This would eliminate the problem of unidentified Bombay patients presenting in emergency, because everyone's blood type would be known from infancy. It would also create an enormous database of rare phenotype individuals who could be counseled, enrolled in autologous donation programs, and connected to specialist management networks. The privacy and ethical implications of such a program are complex, and any extension of genomic newborn screening raises questions that the medical establishment and the broader public need to work through carefully. But the technical possibility exists, and the case for it, from a medical safety perspective, is strong. The cost of identifying a Bombay patient at birth and managing their blood type throughout their life is far lower than the cost of managing a transfusion emergency in an unidentified Bombay patient. Laboratory-grown red blood cells, sometimes called engineered or synthetic red cells, represent another technological horizon. Research programs at several British and international institutions are working toward the ability to manufacture red blood cells in the laboratory from stem cells or other progenitor cells. Such cells can, in principle, be engineered to express whatever antigen profile is desired. An engineered red cell that lacks H antigen entirely would be universally compatible with Bombay-type recipients, solving the compatibility problem definitively. The scale-up challenges are formidable, and this technology is likely many years from clinical routine. But the direction of travel is real, and when it arrives, it will transform the management of not just Bombay blood, but all rare blood phenotypes. There is something that rarely makes it into clinical literature about Bombay blood, and that is what it feels like to be part of the network of people who manage it. Not the patients, not the policymakers, but the people who actually do the work of maintaining connections between Bombay donors and Bombay patients, the individuals who sit at the center of the rare blood web that holds the system together. These are not famous people. They are laboratory scientists, transfusion coordinators, community health workers. They are the people who pick up the phone at unusual hours when a hospital calls with a Bombay patient who needs blood. They are the ones who keep the lists current, who know which donors have moved, which have changed their phone numbers, which have become temporarily ineligible for donation due to travel or illness or medication. They are the ones who coordinate frozen blood transport across the country, who negotiate with airline logistics staff to get units of autologous Bombay blood on a flight from one city to another when a patient has been transferred unexpectedly. The work is largely invisible. When it goes well, no one outside the clinical team knows it happened. The patient recovers. The family is relieved. The surgery was successful. The transfusion was uneventful. What no one sees is the chain of calls and decisions that made the uneventful outcome possible. The coordinator, who realized at 10 in the evening that a patient scheduled for surgery the next morning had a flagged rare phenotype, and that the autologous stock needed to be located and verified. The laboratory scientist who confirmed the Bombay typing on a rushed overnight sample, The donor who agreed to come in the next morning for a fresh donation, even though they had already donated twice in the past year. The networks that support this work are not purely institutional, they are also personal. Bombay blood coordinators in Britain have, over decades of this work, developed relationships with individual donors that go well beyond standard donor service professional contact. These are donors who have been called on multiple times, who have a relationship with specific staff members, who know they are part of a tiny group whose willingness to donate can make the difference between life and death for someone they will never meet. The emotional weight of that is not nothing. Donors who understand the stakes of what they are contributing are more likely to remain engaged, to keep their contact information current, to come in when called even at inconvenient times. The international dimension of these networks is equally striking. The International Rare Donor Program, which connects rare blood registries across multiple countries, has facilitated cross-border blood donations for Bombay patients on a number of documented occasions. Blood has been flown from India to Britain for specific patients. It has been coordinated between British donors and patients in other European countries, where the South Asian diaspora is smaller and Bombay donors fewer. These operations, when they have been required, represent extraordinary feats of coordination across organizational, legal, and logistical boundaries that were not designed to be crossed quickly. The documentary record of these cases, published in transfusion medicine case reports and in presentations at hematology conferences, reads as almost absurdly dramatic if you consider what is actually happening. A surgery that cannot proceed without blood that does not exist in the local supply, calls going out across continents, frozen blood traveling in specialized containers on commercial or charter aircraft, clinicians in 2 countries coordinating across time zones, and at the center of it all, a patient waiting, with family members nearby, for a biological substance that is simultaneously enormously rare and absolutely ordinary, just blood, just the thing that moves through every human being, carrying oxygen from lungs to tissue and carbon dioxide from tissue to lungs, doing nothing more and nothing less than that. The ordinariness of blood and the extraordinariness of the situation around Bombay blood are in constant tension in these stories. The blood itself is not remarkable in any way the patients concerned would ever be able to sense. It looks and moves and functions like any other blood. The H antigen, whose absence defines it, is invisible to any perception other than a specialized immune assay or a molecular test. The Bombay phenotype is a feature of the cell surface at the molecular level, undetectable without laboratory technology, invisible in every lived sense. And yet, it has the power to restructure the logistical priorities of healthcare systems across multiple countries, to animate international networks of scientific and clinical cooperation, to define the medical experience of individuals and families across generations. This disproportionate power of an invisible molecular difference is not unique to Bombay blood. It is characteristic of genetics more broadly. The variants that shape our medical futures are, almost by definition, things we cannot see or feel or taste or smell. They are patterns in a molecular code that is the same in almost every cell of our bodies, a code so densely packed with information that the difference between one person and another is often a single letter changed, or a small section duplicated, or a short segment deleted. These changes are chemically trivial but biologically and medically enormous. They are the kind of thing that makes genetics feel simultaneously precise and arbitrary, the feeling that everything important is happening at a level too small to witness. The philosophical dimension of Bombay blood leads somewhere unexpected if you follow it far enough. Consider what it means that a genetic variant affecting a molecule on the surface of a red blood cell can concentrate in specific communities, not because of any current fact about those communities, not because of anything they have chosen, but because of history. Because of the particular way that human populations have moved across the surface of the planet over tens of thousands of years, because of the specific selective pressures that have shaped different populations in different environments, because of the social structures, including caste systems and community endogamy, that populations have developed in response to those environments. And because of the specific economic and political pressures that drove particular communities to migrate to Britain in particular decades, all of that history, vast, complex, often painful, is stored in the molecular structure of a cell surface antigen in someone walking down a street in Leicester who may never know it is there. History crystallized in biology. The past, written in blood, not metaphorically but literally, in the actual molecular architecture of the cells that carry oxygen through a living body. This is what makes Bombay blood, beneath all its clinical significance, philosophically interesting. It is a window into how human history writes itself into human biology, and how that writing persists across generations and across continents, visible to those with the tools to read it but invisible to everyone else, including to the people whose bodies carry the text. The question of who can read this text, and what they choose to do with what they read, is not a neutral one. Genetic information is powerful in ways that society has not always managed responsibly. The 20th century contains terrible examples of genetic information being used to justify discrimination, exclusion, and violence. The 21st century has produced new concerns about genetic privacy, about insurance discrimination, about the use of genomic data by employers and government agencies in ways that were not consented to and not anticipated. These concerns are legitimate and serious. But the answer to the misuse of genetic information is not the suppression of genetic knowledge. It is the development of ethical frameworks for the use of that knowledge that protect individuals while allowing the genuine medical benefits of genetic understanding to be realized. Bombay blood is a case where genetic knowledge is medically essential. Not knowing you are Bombay type is not a neutral state. It is a state of potential danger. The appropriate response to that danger is to ensure that affected individuals know their status, understand the implications, and are connected to the medical resources that can protect them. That requires both genetic knowledge and the social and institutional capacity to deploy that knowledge responsibly. Britain has made progress on both fronts, though the progress is uneven and the work is incomplete. The genetic understanding of Bombay blood is better now than it was in 1952, or in 1972, or in 1992. The molecular basis of the condition is well characterized. The population genetics behind its distribution in British communities are increasingly understood. The clinical protocols for managing Bombay patients are more developed and more reliably implemented than they were in earlier decades. And the community engagement programs that identify affected individuals before crises occur are more effective than they were when they were first attempted. None of this is finished. None of it is complete. There are still Bombay-type individuals in Britain who do not know they are Bombay-type. There are still hospitals outside the major cities that would be badly wrong-footed by a Bombay emergency. There is still a shortage of registered Bombay donors relative to the probable size of the Bombay population in Britain. There is still a gap between the level of community awareness that exists in South Asian communities about this issue and the level that would ideally exist. These are real limitations, and they represent real risks for real people. But the direction of travel is positive. The tools are improving. The networks are developing, the awareness is growing, and the underlying principle that is driving this progress is the right one. A healthcare system exists to serve the population it has, not the population it imagines or the population it was designed for when it was founded. The population it has is diverse, biologically as well as culturally. That diversity is a product of history, of movement, of the human story in all its complexity. Responding to that diversity appropriately is not a concession or an accommodation in any diminishing sense. It is the core work of medicine. It is what medicine is for. To think about Bombay blood in Britain is to think about all of this at once. The molecular biology and the population genetics, the migration history and the community structures, the institutional response and its limitations. The human stories of individuals discovering their blood type and navigating a medical system that was not built with them in mind. The networks of scientists and coordinators and donors who hold the practical management of this condition together, and underneath all of it, the vast, slow process of human movement across the planet, the way populations have mixed and separated and carried their biology through thousands of years of history, depositing genetic signatures in unexpected places, concentrating rare variants in communities formed by forces that had nothing to do with genetics and everything to do with politics, economics, and the endless human search for safety and opportunity. Britain is, in this reading, not simply a country where Bombay blood happens to be more common than elsewhere. Britain is a place where the genetic history of the world has been partially deposited. A country that has absorbed, over the course of its history, migrants from nearly every population on Earth, each carrying their specific genetic heritage, their specific rare variants, their specific medical needs. Bombay blood is one of the most striking examples of what this looks like at the level of a specific molecular marker. But it is part of a much larger picture of genetic diversity that is itself part of an even larger picture of human movement, human history, and the unending negotiation between the biological past and the medical present. This negotiation is never finished. New communities will arrive, carrying their own genetic heritages, their own rare variants, their own medical needs that the existing system does not yet know how to accommodate. The institutions will need to update. The knowledge will need to expand. The community partnerships will need to be rebuilt for new communities with different histories and different contexts. The work is ongoing, and it is necessary, and it is, in the deepest sense, what it means for a society to take seriously the obligation to care for all of its people, rather than only the ones it originally anticipated. There is one more dimension of Bombay blood's story in Britain that deserves consideration, and it is the one that connects most directly to the oldest questions that humans have ever asked about themselves. The questions asked around fires 40,000 years ago, the questions carved into cave walls, the questions buried with the dead along with red ochre and grave goods and flowers, the questions about who we are, where we come from, and how we relate to each other across the distances of time and space. Genetics, in the modern era, has become one of the primary tools by which people answer these questions about themselves. Ancestry testing services have become enormously popular, partly because they tap into the deep human desire to know the story behind one's own existence. Where did my grandparents really come from? What populations are in my heritage? What is the history that I carry but cannot directly remember? These are ancient questions, and the modern genomic tools that address them feel genuinely revelatory to most people who use them, even knowing that the answers are statistical and probabilistic rather than certain and complete. Bombay blood is an extreme case of genetic self-knowledge. It is not a probabilistic ancestry estimate. It is a hard fact about a specific molecule on the surface of a specific cell type. You either have it or you do not. But, like ancestry testing, it connects the person who receives the information to a history much larger than their individual life. Finding out you are Bombay type is finding out that you carry a genetic variant shaped by specific population histories, maintained by specific social structures, distributed by specific patterns of migration. It is finding out that your body is a product of history in a way that most people never have occasion to confront so directly. This can be a disorienting discovery, or it can be an orienting one, depending on how it is framed and received. The disorientation comes from the medical implications, from the sudden sense of vulnerability, from the complexity of the medical landscape that a Bombay diagnosis opens up. The orientation comes from the connection it creates, from the sense that you are part of a community of people who share not just this rare variant, but the history that produced it, the migrations, the social structures, the centuries of specific human experience that concentrated this particular molecular signature in your particular lineage. The South Asian communities in Britain that carry elevated frequencies of Bombay blood are also communities with extraordinarily rich and complex histories. They carry the history of the Indian subcontinent's ancient civilizations, of its medieval kingdoms and its Mughal empire, of its encounter with European colonialism and its long resistance to it. They carry the history of the East India Company and of the independence movement. They carry the history of partition and its violence. They carry the history of the specific migrations that brought their families to Leicester and Birmingham and Bradford, the hopes and the difficulties, the displacement and the adaptation, the maintenance of culture and language and practice across generations in a new country. Bombay blood is a thread within all of this history. A small thread, a molecular thread, invisible to every sense except a specialized laboratory assay. But it is a thread that connects the molecular to the historical in a way that few medical phenomena can. It is a case where the story of a specific gene in a specific community of people in a specific country is also, when traced far enough, the story of thousands of years of human movement across the surface of the planet. The kind of story that starts very small and opens into something enormous. And it is a story that is ongoing. The Bombay-type individuals living in Britain today are not the end of the story. Their children and their grandchildren will inherit their genetic variants or will not, depending on the specific combination of their parents' genotypes and on the probability distributions of inheritance. Some Bombay-type individuals will have children who are also Bombay-type. Others will have children who carry one copy of the FUT, one mutation, but express normal phenotype. Others, if they partner with someone who carries no FUT1 mutations, will have children who carry one copy and may or may not pass it on in turn. The genetics are Mendelian, governed by the same laws of inheritance that Gregor Mendel worked out in his monastery garden in the 19th century, using pea plants that had no idea they were contributing to the understanding of heredity. The future of Bombay blood in Britain will be shaped by decisions that are being made now. Decisions about healthcare investment and about rare donor programs and about genomic newborn screening. Decisions about community outreach and about cultural competence in healthcare provision. Decisions by individual Bombay-type people about whether to predonate autologous blood, whether to carry medical identification, whether to inform family members who should be tested. Decisions by researchers about where to direct scientific effort, about how to develop the laboratory-grown blood technologies that could eventually eliminate the compatibility problem entirely. All of these decisions matter. None of them are trivial. The woman who carries Bombay blood and does not know it is also making a decision, by default, simply by going about her life without the information she needs. The healthcare system that has not yet reached her with a screening program or an awareness campaign is making a decision too about priorities and resources and who the effort is directed toward. These are not neutral states. They are choices, with consequences that may someday manifest in an emergency room at a moment when there is no time left for deliberation. The best outcome, the one that the people who work in rare blood management in Britain are working toward, is the one where the invisibility is resolved before the crisis, where the woman who carries Bombay blood finds out in a planned, supported, contextualized way, where her family members are tested, where her autologous blood is in frozen storage somewhere, waiting for a need that may never come but that is prepared for regardless, where the healthcare system has done its job not just in responding to emergencies but in preventing them, in giving people the information they need to protect themselves. That is not a utopian vision. It is an achievable one, given the tools that now exist and the institutional will to use them. The tools are better than they have ever been. The understanding is deeper than it has ever been. The community networks that make outreach possible are more developed and more trusted than they were in earlier decades. What remains is the will to continue the work, to maintain the investment, to keep the partnerships active, and to understand that the story of Bombay blood in Britain is not an unusual problem requiring a temporary solution, but a permanent feature of a diverse society that requires permanent, sustained, responsive engagement. There is something in the story of Bombay blood that speaks to something deeper than medicine. It speaks to what it means to know someone, to really know them, not the surface of them, not the history they can tell you directly, not the identity they present in conversation or in the stories they choose to share, but the history that is written in them below any surface anyone can see, below any story anyone can tell, in the molecular structure of the cells that keep them alive, in the specific variants that distinguish them from the 5 billion or more other humans currently alive, and connect them to the specific ancestors who carried those variants before them. None of us can read that history directly. We do not experience ourselves as genetic texts. We experience ourselves as people, as bodies moving through the world, as minds processing experience, as members of families and communities and cultures. But the genetic history is there, in every cell, in every red cell moving through every vessel, carrying oxygen and carrying history simultaneously, neither of them visible to the naked eye, both of them real, both of them mattering in ways that reveal themselves only when the conditions are right. For most of us, the genetic history stays invisible our entire lives. We live and die without ever confronting the specific molecular architecture of our red cell surfaces in any clinical context. We are blood types we never think about, carriers of variants we never know, vessels for histories we never articulate. Our blood does its work and we do ours, and the two stories never quite touch. But for some people, a small number, a number that in Britain is measured in the hundreds rather than the thousands or millions, the genetic history does break through. It becomes visible, It becomes clinically relevant. It becomes the thing that changes how they must navigate medical care, how they must think about their own bodies, how they must communicate with a system that was not designed with them in mind. It becomes, in the fullest sense, their own story rather than just background. And when it does, the story it tells is always the same story. The story of where they come from, in the deepest possible sense. The story of every generation before them that lived and moved and reproduced and carried forward the specific biological heritage that eventually, through chains of history and chance and selective pressure and migration and community structure, arrived in them. That is what Bombay blood is. It is that story, made molecular, invisible until it is not, old as the populations that carry it, new as the medicine that can now read it. And in Britain, in the specific historical and demographic context that makes Britain's situation unusual, it is a story about how deeply the lives of millions of people from the other side of the world are written into the biological fabric of this island. Not metaphorically, not culturally, but literally, molecularly, in the actual blood of actual people living in actual cities, where blood banks keep lists and coordinators make calls and donors come in and the network holds, imperfectly but genuinely, against the emergencies that none of them can entirely prevent, but all of them work, every day, to manage. The person with Bombay blood walking down a street in Leicester does not know what they carry, but someone knows that people like them exist. Someone is maintaining the list. Someone is keeping the frozen stock. Someone is answering the phone when the call comes. And that's what medicine at its best looks like. Not the dramatic moments, though those exist. The steady, patient, quiet history moving through blood. And somewhere in between, the human effort to understand both well enough to help. To sit with all of this, and to really hold it, you need to let the numbers recede for a moment and let the human scale come forward. Not the frequency statistics, not the population genetics models, not the clinical protocols. Just the fact that, somewhere in Britain right now, probably in multiple cities simultaneously, there are people who carry Bombay blood and who are going about their days with no particular awareness that anything about them is unusual. One of them might be sitting in a waiting room right now, waiting for a routine appointment. Another might be on a bus, going home from a shift. Another might be cooking dinner, or helping a child with homework, or watching television, or trying to get to sleep. None of them feel different. None of them experience any subjective sense of their unusual biology. They are, in every way that they can access directly, entirely ordinary people. And within each of them, 4,500 times a second, give or take, their hearts are pushing blood through an elaborate network of vessels, and that blood is doing everything blood is supposed to do, carrying oxygen and nutrients and immune cells and clotting factors and all the molecular machinery of survival. Doing it perfectly, doing it without any assistance from anyone, doing it because evolution built them to do it. The blood does not know it is Bombay blood. It does not know it is unusual. It does not know that its H antigen-free surface distinguishes it from the blood of 99.9% of the humans on the planet. It simply moves. It simply does its work. The strangeness of Bombay blood, the whole medical and genetic drama of it, exists only in the encounter between that ordinary blood and a medical system that has built its categories around the majority. The blood is not wrong. The person is not broken. The situation is simply one in which the categories that the medical system developed to serve the majority, the ABO system, the AH system, the assumptions about what blood looks like and how it behaves, do not quite capture the full range of what human blood can be. This is, in a way, a parable about categories, about the way that any system of categories, however well designed, will eventually encounter phenomena that do not fit. The ABO blood typing system was designed to prevent transfusion deaths, and it has succeeded enormously in that goal. But it was designed around the biology of the populations its designers knew, and those populations did not include a significant presence of people with Bombay blood. The system had a blind spot, and the expansion of its user base revealed that blind spot. Every system has blind spots. The question is not whether a system will eventually encounter cases that fall outside its categories, but whether the system is designed to recognize and respond to those cases when they appear, or whether it treats them as anomalies to be dismissed or managed badly. A system that recognizes its own limits, that has built-in mechanisms for identifying cases that fall outside standard categories and escalating them appropriately, is a safer system than one that assumes its categories are exhaustive. British transfusion medicine has, over the 70 years since Bombay blood was first described, been building such mechanisms, imperfectly, with considerable lag, and with ongoing gaps that real people are still falling through. But the direction of movement has been toward greater recognition of biological diversity, not away from it, and the communities whose biological diversity was least visible in the original framework are gradually, too slowly, being brought into the frame. To understand why Britain has more Bombay blood than almost any other country on Earth is to understand how history accumulates. It accumulates in policies and in economics, in the decisions of colonial administrators and the responses of colonized people, in the routes of ships and the availability of employment and the networks of kinship that guide migration. It accumulates in social practices, in marriage customs that persist across continents and generations, in community structures that maintain genetic coherence in diaspora settings. And it accumulates, finally, at the molecular level, in the cell surfaces of individual people who are the living downstream consequences of all this accumulated history. That person in Leicester, walking down the street, does not experience herself as a downstream consequence. She experiences herself as a person, with her own life, her own choices, her own identity. But she is also, inescapably, a biological record of everything that preceded her. Her cells know things her mind does not. Her blood carries information that she cannot directly access, but that a well-equipped laboratory can read with considerable precision. And that information, that molecular record of where she and her ancestors have been and how they have lived, is part of what makes her who she is at the deepest biological level. None of this diminishes her. None of it makes her less than any other person. If anything, the story of Bombay reveals how rich and complex and historically embedded every human being actually is. We are all archives of history. We all carry in ourselves the evidence of migrations and adaptations and demographic events that we have no direct knowledge of and that are not part of any story we consciously tell about ourselves. Bombay blood is simply a particularly clear window into this fact, one that becomes visible because a specific molecular marker is being tracked by a medical system with the tools to detect it. The window is small, and what it reveals is a fraction of the total. But the fraction is enough to see the principle. Enough to understand that the blood moving through every human body on Earth is carrying history alongside the oxygen, that the past is present in us at the molecular level, and that understanding that presence, learning to read it, learning to respond to it appropriately and responsibly and with genuine care for the people whose blood carries it, is part of what it means to be a society that takes seriously its commitment to all of its members. The woman with Bombay blood is, in the end, not defined by her blood type. She is defined by all the things that make her a person, by her relationships and her choices, and her experiences, and her contributions, and her presence in the lives of people who know her. But her blood type is part of the full picture of who she is, part of the biological reality that a healthcare system must account for if it is to serve her properly. It is a small part of a vast and complex human truth, but it is real. It is there, and it matters, in the quiet, ordinary, essential way that everything biological matters, which is that it is the foundation on which everything else is built. The final thought, the one that stays with you when you have followed this story all the way through, is not about medicine or genetics or migration, though it has passed through all of those. It is about how thin the line is between the ordinary and the extraordinary, about how a single molecular feature, invisible and unfelt and unknown until the right laboratory test reveals it, can be the thing that determines whether a person in an emergency lives or dies, about how the vast machinery of human history, with all its scale and complexity and violence and movement, can ultimately crystallize into something as small and specific as a cell surface protein, or the absence of one, about how much of who we are, really, is written in language we cannot read without tools we invented very recently, in a body that has been carrying that text since before any of our conscious histories began. This is not a comfortable thought, exactly. But it is a true one. And truth, even when uncomfortable, is the thing that ultimately serves people better than any available alternative. The people who work in rare blood management know this. The researchers who study population genetics know this. The community health workers who carry these conversations into homes and mosques and community centers and try to explain, in plain language and with genuine care, why it matters that someone get tested, why it matters that blood be pre-donated, why the network exists, and why it needs them to be part of it. They know this too. They are all, in their different ways, working with the same fundamental truth, that human beings are biological creatures with histories written into their cells, that those histories create specific vulnerabilities and specific needs, and that meeting those needs requires understanding those histories with real depth and real care, and that Bombay blood is the specific case. The general truth is what it reveals. And the general truth is that caring for people, really caring for them, begins with understanding what they carry, where it came from, and what it means for who they are and what they need. That is the story of Bombay blood in Britain, and it is, like all the best stories, both very small and very large, a molecule and a migration, a cell surface and a century of history. A person walking down a street in Leicester, and the 40,000 years of human movement that brought her and her ancestors to exactly this place and this moment. All of it present simultaneously, all of it real, all of it, if you know where and how to look, legible in the blood. The city of Leicester sits in the English Midlands, roughly equidistant from London and Birmingham, and it does not immediately present itself as a place where you would go looking for answers to questions about molecular biology or ancient migration. It is an ordinary English city in most of its visible dimensions. Red brick and concrete, shopping centres and bus routes, the usual English mixture of the very old and the very recently built, churches from the medieval period and supermarkets from last decade, all existing in the kind of dense, pragmatic coexistence that English cities have always managed. But Leicester is also, depending on how you count, either the most or among the most ethnically diverse cities in the United Kingdom. It was one of the first cities in Britain to have a majority non-white population, a demographic milestone that it crossed sometime in the early 2000s. Its South Asian community is particularly large and historically established, with deep roots going back to the first waves of East African Asian arrivals in the early 1970s, when Idi Amin expelled the South Asian community from Uganda and large numbers of those families, many of them holding British passports, settled in Leicester. Those families were overwhelmingly Gujarati, and they built in Leicester one of the most concentrated and culturally robust Gujarati communities outside of Gujarat itself. Leicester's Golden Mile, the stretch of Belgrave Road lined with Indian restaurants and sweet shops and jewelers and sari shops and temples, is one of the most widely known South Asian commercial streets in Britain. It represents not just cultural presence but the economic and social infrastructure of a community that is now into its third and fourth generations in the city. Children born in Leicester to parents born in Leicester to grandparents who came from Kampala or Nairobi or Ahmedabad are as Leicester as anyone in the city, and they are also carrying the genetic heritage of those Gujarati ancestors, including whatever genetic variants, rare or common, were present in the specific communities from which those families originated. The genetic significance of Leicester's Gujarati community has been noted in medical genetics contexts, specifically because of conditions like Bombay blood. The community represents a large, geographically concentrated population drawn from specific South Asian origins, with a degree of internal community cohesion that has maintained some genetic continuity with those origins across multiple generations in Britain. This makes Leicester, along with Birmingham and parts of London, one of the most likely places in Britain to find elevated frequencies of genetic variants that are elevated in Gujarati South Asian populations. The blood transfusion service serving Leicester is aware of this. The haematologists and transfusion medicine specialists working in Leicester's hospitals have, over the years, developed protocols and procedures that account for the demographic reality of the city's patient population. They have seen more rare phenotype cases, including Bombay blood cases, than comparable services in cities with different demographics. They have built more expertise. They have more established relationships with community organizations. They know, in a way that services in more homogeneous cities do not always know, that the standard framework for blood typing needs to be extended, enriched, made responsive to the actual biological diversity of the people walking through their doors. This expertise is not automatic. It was not given to Leicester because of some wise policy decision made at a national level. It developed because the city's demographics created a reality that the local medical establishment had to respond to, and respond to repeatedly, over many years. The expertise is embedded in individuals, in the specific knowledge of specific consultants and laboratory scientists who have worked in Leicester for decades, who have managed Bombay cases and other rare phenotype cases, and have accumulated clinical wisdom that exists nowhere in any guidelines document because it is too granular, too specific, too rooted in the particular demographic context of this particular city to be easily codified. When those individuals retire, that expertise does not automatically transfer. This is one of the structural vulnerabilities of rare phenotype management in the British NHS. The knowledge is too often held by individuals rather than embedded in systems. A laboratory scientist who has managed Bombay blood cases for 30 years knows things that are not written down, that cannot be easily conveyed in a handover document, that exist only in the accumulated pattern recognition of decades of practice. When they leave, a piece of the institutional memory leaves with them. The systems that should capture and preserve that knowledge are not always adequate. This is not a unique problem to blood transfusion medicine or to rare phenotypes. It is a general problem of specialized expertise in any large organization. But for something as rare and as consequential as Bombay blood, the loss of expert individuals can have real effects on patient safety in the specific institutions where those individuals worked. The answer, at the institutional level, is better documentation, better knowledge management systems, better training programs that transfer expertise from experienced practitioners to those who will follow them. These are solvable problems. They require resources and attention and the kind of organizational commitment that is sometimes lacking when the condition being managed affects a small number of patients. The small number argument is one that haunts rare disease medicine generally. When the affected population is measured in hundreds rather than thousands or millions, the case for large-scale institutional investment is harder to make. The resources required to properly manage Bombay blood in Britain, to screen communities, maintain donors, store autologous blood, train clinical staff, maintain the coordination networks, are significant relative to the number of people directly affected. The cost per patient is very high by any standard health economic measure. The counter-argument is not primarily utilitarian. It is not that the cost per Bombay patient is actually lower than it appears when all factors are considered, though that case can be made. It is that a healthcare system's commitment to serving all of its members cannot be contingent on how many of them share a particular need. The person with Bombay blood has the same right to appropriate medical care as the person with the most common blood type in the country. Their relative rarity does not diminish that right. A society that abandons its commitment to individuals when serving those individuals is expensive is not really committed to caring for its members. It is committed to caring for them conditionally, and conditional commitment is a fragile foundation for a healthcare system. This is the philosophical case that the NHS, at its best, has always made for itself, that the commitment is unconditional, that it extends to everyone regardless of what their care costs or how unusual their needs are. The practice has never fully matched the principle. There have always been rationing decisions, prioritization choices, resource constraints that mean the principle is imperfectly realized. But the principle matters. It creates a direction of travel, a standard against which performance can be measured and shortfalls can be identified. For Bombay blood, the direction of travel has been generally positive. The shortfalls are real, but are being addressed. The standard has not been abandoned. And the work continues, patient by patient, donor by donor, call by call, frozen unit by frozen unit, in the quiet networks of people who have made it their professional concern to ensure that people with unusual blood can receive the care they need. To spend time thinking about Bombay blood is, in the end, to spend time thinking about what connects us. The molecular connections, the genetic threads running through populations separated by oceans and centuries. The historical connections, the long chains of cause and effect that link decisions made in 19th century Bombay to outcomes in 21st century Leicester. The medical connections, the networks of donors and coordinators and laboratories that form a web of protection for a small number of people with unusual needs. And the human connections, the fact that every Bombay donor who gives their rare blood is contributing to the survival of a stranger they will never know, purely because their biology makes them capable of helping in a way that almost no one else can. This is the deepest story that Bombay blood tells, not the story of a medical anomaly or a population genetics curiosity. The story of how, at the molecular level, we are connected to each other and to our histories in ways that are invisible but real, that are silent but consequential, that are ancient but urgently present. The blood that flows through every human body is carrying all of this simultaneously. History and oxygen, migration and hemoglobin, the past and the present, indistinguishable at the molecular level, inseparable in the actual lived reality of the people whose blood it is. This is what Bombay blood means. This is why it matters that Britain has more of it than almost any other country on earth, not as a source of worry or alarm, not as an argument about migration or community or belonging or any of the other politically charged framings that these facts could be dressed in, but as a window into the extraordinary richness and complexity of what it means to be human in a world shaped by thousands of years of human movement, human history, and the unending biological reality that all of that history leaves behind. The blood remembers, even when we have forgotten, even when the history that shaped it is distant and strange and hard to reconstruct, even when the people whose blood it is have no conscious connection to the migrations and the communities and the selective pressures that determined its molecular architecture, the blood remembers. And now, because of the science, we can remember with it. We can read the record that it carries. We can understand, at least partially, what it means, and we can use that understanding to care for the people who carry it, which is the most important thing that understanding is for. The history of blood in medicine is longer and stranger than most people realize. For most of human history, blood was understood almost entirely in symbolic terms. It was life, obviously, because its loss meant death. It was identity, because it was inherited, because the blood of a family was thought to carry the essence of that family's character, its nobility or its commonness, its virtue or its vice. It was the currency of kinship, the medium through which ancestry was transmitted from generation to generation. When people spoke of bloodlines, they were using a metaphor that they took quite literally, imagining the actual liquid substance of blood as the vehicle through which everything important about a person was passed from parent to child. This is not an ancient idea that modern science has simply replaced. It is an ancient idea that modern science has transformed, but not entirely. The transformation is real, and it is profound. We now understand that blood does not carry character or virtue or the specific qualities that make a family in any social sense. What blood actually carries, in biological terms, is a set of cells and proteins, including various molecules on the surfaces of those cells that constitute the blood group antigens, and a copy of roughly the same genetic information that is present in every nucleated cell of the body. The idea that blood transmits identity is not wrong, exactly, but it is radically different from what people thought they meant when they said it. The identity transmitted is genetic, not social or moral, and it is transmitted through the entire genome, of which blood group antigens are a tiny fraction. But the symbolic resonance of blood as identity has never gone away. It persists in language, in the phrases we reach for without thinking about their origin. Bloodline, blood tie, blood relative, in my blood, bad blood, blue blood, full-blooded. These phrases carry weight that exceeds their literal meaning precisely because they tap into something deep in how human cultures have always understood themselves and their relationships. Blood has always been the language of belonging. The story of Bombay blood lives in both registers simultaneously. In the scientific register, it is a story about a molecular variant in a specific gene on chromosome 19, about the population genetics of how that variant became elevated in certain communities, about the clinical implications of its presence in a modern healthcare context. In the symbolic register, it is a story about blood as identity, about how specific communities carry their histories in the most intimate possible way, in the cells of their own bodies, and about how those histories become visible when science has developed the tools to read them. Neither register fully contains the story without the other. The purely scientific account strips away the human meaning of the genetics, treating the FUT1 mutations as interesting only insofar as they create clinical problems or population genetics puzzles. The purely symbolic account loses sight of the actual molecular reality, allowing the language of blood and identity to operate at the level of metaphor while the actual biology goes unexplained. The most complete understanding holds both together, seeing the molecular reality for what it is, while also seeing what it means for the people and communities involved. This kind of two-level understanding is difficult. It requires holding scientific precision and human meaning in the same frame simultaneously. It requires resisting the temptation to flatten the story into either pure science or pure narrative. And it requires a certain comfort with the fact that important stories are always complicated, always resistant to single-sentence summaries, always full of threads that lead in multiple directions and never quite converge on a single simple point. The story of Bombay blood in Britain is exactly this kind of story. It starts with a molecule and ends with a community. It begins with a laboratory finding in 1952 and leads to decisions being made today about healthcare policy and donor recruitment and genomic screening programs. It involves population genetics and the history of the East India Company. It connects the molecular biology of red cell surface antigens to the sociology of endogamous marriage in South Asian communities. It links the clinical protocols of NHS blood and transplant to the ancient demographic history of populations on the Indian subcontinent. Every thread you pull generates more threads, and none of them are irrelevant. What does it mean for a country to have, in its blood banks and its hospital registries, a record of its own demographic history? Because that is what the distribution of rare blood phenotypes in Britain represents. A biological record of who has come to Britain, from where, and when. The elevated frequency of Bombay blood in British South Asian communities is, from one angle, a medical management challenge. From another angle, it is a kind of archive. A molecular archive of the specific migrations that created the current composition of the British population. An archive that was not designed as such, that was never intended to serve as historical documentation, but that functions as historical documentation nonetheless, because biology does not forget even when institutional records are incomplete or the human memories of those involved have faded. This archival function of population genetics is something that researchers in the field have been exploring with increasing sophistication over the past 2 decades. Ancient DNA studies, which extract and sequence genetic material from the bones of individuals who died hundreds or thousands of years ago, have transformed our understanding of prehistoric population movements. The populations that inhabited Britain before the Romans, before the Saxons, before the Normans, can now be characterized genetically in ways that were completely impossible a generation ago. The waves of migration that shaped the British genome are visible in the ancient DNA record, each wave leaving its signature in the frequencies of specific alleles across the genome. Modern DNA studies, examining the genetic composition of living populations, extend this analysis into the much more recent past. The genetic signatures of more recent migrations, including the South Asian migration of the 20th century, are visible in the genomes of British South Asian individuals and, to a progressively smaller degree, in the genomes of their children, grandchildren, and subsequent generations, as intermixing with the broader British population dilutes the specific South Asian genetic signal. Bombay blood is one particularly striking marker in this more recent layer of the genetic archive, not because the migrations it marks are unique, but because the specific variant is rare enough and concentrated enough to be a clear signal rather than background noise. The archive is not passive. It is being actively read by the scientists who study population genetics in Britain. It is being used to understand not just migration history, but the distribution of medically relevant genetic variants, the identification of populations at elevated risk for specific conditions, the planning of targeted screening programs. The information in the archive serves practical purposes that directly affect the health of living people. This is not an abstract or academic exercise. It is translational research, moving from population-level genetic understanding to individual-level clinical application. One of the most important translational applications in the context of Bombay blood is family counseling. When a Bombay phenotype individual is identified, the most immediately useful thing the healthcare system can do, beyond managing that individual's own care, is to identify and counsel their relatives. Siblings of a Bombay phenotype person have a significant probability of also being Bombay phenotype, depending on the genotypes of their parents. If both parents are heterozygous carriers, each sibling has a 1 in 4 chance of being Bombay phenotype. If one parent is Bombay phenotype and the other is a heterozygous carrier, the probability rises to 1 in 2. This arithmetic is well understood, but its implementation in clinical practice is less consistent than it should be. Cascade screening, the systematic extension of genetic testing from an identified individual to their relatives, is a standard practice for several genetic conditions in the NHS. Familial hypercholesterolemia, BRCA gene mutations associated with breast and ovarian cancer, certain cardiac arrhythmia disorders. Bombay blood, which is less common than any of these, has not historically been the subject of the same systematic cascade screening approach. The infrastructure for it is less developed, the clinical genetics support is less established, and the awareness among the clinicians most likely to encounter Bombay cases is less uniform. This is a gap that represents real risk. A Bombay phenotype individual, who is identified, but whose siblings are not tested, is surrounded by relatives who may be Bombay phenotype themselves and who are no safer than the index case was before their own identification. The identification of one Bombay person is an opportunity to identify others, and that opportunity is not always fully exploited. Every missed opportunity is a person who remains unidentified, whose next medical emergency may unfold without the preparation that their blood type requires. The NHS has been moving toward better cascade screening infrastructure for rare conditions generally, but the pace is slow and the implementation is uneven across regions and across conditions. Rare blood phenotypes are not high on the priority list for cascade screening programs because the clinical genetics infrastructure tends to be focused on conditions with more straightforward inheritance patterns and more established disease associations. Bombay blood, which is definitively inherited, but which does not cause disease in any direct sense, which is a clinical risk factor rather than a disease itself, occupies an awkward position in the taxonomy of genetic conditions and is sometimes lost in the gaps between transfusion, medicine, and clinical genetics as specialties. The solution to this kind of structural gap is coordination, which sounds trivially obvious but is genuinely difficult in a large, complex healthcare organization with separate funding streams, separate specialist silos, and competing priorities for limited resources. Coordination between transfusion medicine and clinical genetics, between hospital hematology departments and primary care, between NHS specialist services and community health outreach programs, between the registries maintained by NHS Blood and Transplant and the electronic health records maintained by GP practices and hospital trusts. Each of these connections exists to some degree, but none of them is seamless, and the gaps between them create the spaces where individuals fall through. Improving these connections, making them more robust, more reliable, more systematically maintained, is the kind of unglamorous institutional work that determines whether healthcare systems actually function for the people who need them. It is not the kind of work that generates headlines or wins prizes. It is the work of maintaining systems, of updating databases, of following up on flagged cases, of ensuring that the right information reaches the right person at the right time. It is, in a very real sense, the most important work that healthcare systems do because it is the work that determines whether the impressive capabilities that the system possesses in principle are actually accessible to the people who need them in practice. For Bombay Blood, this institutional work is the difference between a system that can identify and protect people with this rare phenotype and one that identifies them only when they are already in crisis. The aspiration is the former. The reality, in Britain today, is somewhere in between. Progress is real. The gap between aspiration and reality is real too. And the people who care about rare blood phenotypes, who have dedicated their careers to understanding and managing them, are working in that gap every day. The gap will narrow. It always has, in the history of how medical systems learn to respond to biological diversity. The process is slow and imperfect, and sometimes requires tragedy to accelerate. But the direction of movement is clear, and the tools available now, including molecular typing, genomic screening, improved database technology, and more sophisticated community engagement approaches, are better than they have ever been. The story of Bombay blood in Britain is not finished. It is being written every day, in the decisions of healthcare policymakers, and in the actions of community health workers, and in the choices of individual donors and patients. Every chapter that is being written now will be part of what future generations understand about how a diverse society learned to account for the biological complexity that its diversity creates. Consider for a moment what it would mean to live in a body that medicine does not yet know how to serve. Not because your condition is untreatable in any medical sense, not because the knowledge to help you does not exist somewhere in the world, but because the specific configuration of need and knowledge and resources in the place where you happen to be means that the help that exists in principle is not reliably available to you in practice. This is the situation that Bombay blood creates for affected individuals in parts of Britain where the infrastructure for managing rare blood phenotypes is thin, and it is a situation that matters more than its low statistical frequency would suggest, because the moment when it matters is the worst possible moment, the moment of medical emergency, when every minute is urgent, and the systems that are supposed to protect you are the systems you most need to function. The psychological weight of living with this knowledge, once you have it, is something that clinicians and counselors who work with rare blood phenotype patients describe with real care. The transition from not knowing to knowing is almost always described by patients as significant, in some cases as profoundly disorienting. You have lived your entire life up to this point without giving your blood type any more thought than you give to the particular shade of your hair or the specific size of your hands. It was background information, fixed but irrelevant to any decision you ever made. And then suddenly it is not background. It is the most important medical fact about you, the one that will structure how you engage with healthcare for the rest of your life. The practical implications cascade out from the initial discovery in waves. The first wave is immediate and clinical. What does this mean for any surgery I might need? What do I do if I am injured? Who needs to know about this? The second wave is familial. Which relatives should be tested? How do I have this conversation with my parents, my siblings, my children? The third wave is social and institutional. How do I ensure that this information is properly recorded in my medical notes? How do I access the autologous donation program? What should I carry with me when I travel? The fourth wave is existential, and this is the one that people who counsel rare blood phenotype patients describe as the most enduring. What does it mean that my body works differently from almost everyone around me, in a way I can never see or feel or know directly, that exists only in the gap between my cells and a standard blood transfusion? This existential dimension is not unique to Bombay blood. Anyone with a condition that is invisible, that does not manifest as illness in ordinary life, but that creates specific medical risks under specific circumstances, navigates some version of this. People with severe allergies, people with certain cardiac conditions, people with factor V Leiden or other clotting disorders. The invisible condition that is not a disability until suddenly it is, that does not interfere with daily life until suddenly us, creates a specific psychological relationship with the body that is different from both chronic illness and from ordinary health. The support available for Bombay blood patients navigating this existential dimension is, in honest assessment, thin. The clinical infrastructure for managing the medical aspects of the condition has improved significantly over the decades. The psychological and social support for living with the knowledge of the condition has not kept pace. Most Bombay patients receive their diagnosis in the context of a transfusion medicine consultation, which is focused on the medical management of their blood type, and not primarily on the psychological adjustment to having this information. The brief counseling that happens in those consultations is valuable but limited. It covers what the patient needs to do, not what they might need to feel or process or work through in the months and years after the initial disclosure. Patient support groups for rare blood phenotypes exist in some countries, and there are online communities where people with unusual blood types connect with others who share their situation. These informal networks serve a real function. They allow people to share practical knowledge, to swap experiences of navigating healthcare systems with unusual blood types, to feel less alone in what is, by definition, a very uncommon situation. But they are not a substitute for formal support structures, and the awareness of their existence is low among the healthcare providers who counsel Bombay patients and could direct them toward these resources. The comparison with other rare conditions is instructive here. Conditions that affect similar numbers of people, rare cancers, rare genetic syndromes, rare immunological disorders, have generally attracted more organized patient advocacy and support infrastructure than rare blood phenotypes. Part of the reason is that those conditions manifest as illness, as symptoms that are experienced, as suffering that is visible, and that generates a clear motivation for advocacy and for the building of patient communities. Bombay blood does not make you ill. It makes you at risk. And risk, particularly invisible risk, does not generate the same degree of patient community mobilization that illness does. This is a gap that matters for the management of Bombay blood at the population level. Well-organized patient communities are one of the most effective mechanisms for disseminating information, for maintaining donor engagement, for advocating for better healthcare infrastructure, and for providing the peer support that reduces the psychological burden of living with the knowledge of a rare condition. The absence of a strong Bombay blood patient community in Britain means that individuals who receive this diagnosis are more isolated with it than they might be if the community infrastructure were better developed. They are more dependent on the institutional channels of the healthcare system and less able to draw on the knowledge and experience of others who have been through the same process. Building such a community is not impossible. It requires coordination and resources, and a recognition by the institutions involved that patient advocacy and peer support are healthcare functions, not add-ons to real medicine. The increasing use of digital platforms and social media has made it easier to connect small numbers of people with uncommon conditions than it was before. The South Asian communities where Bombay blood concentrates in Britain are communities with strong internal communication networks and with experience of organizing around shared community concerns. The infrastructure for a Bombay blood community in Britain exists in fragments. What it needs is the catalysis to bring those fragments together. The story of how rare disease communities have organized and advocated for themselves in the 20th and 21st centuries is one of the most remarkable stories in the history of medicine. Conditions that were once managed purely by doctors acting on patients who had little information or agency have been transformed by patient advocacy into conditions where the affected communities are active participants in research, design, treatment, development, and policy formation. The HIV/AIDS activist community in the 1980s and 1990s is the most famous example, but the pattern applies across many rare conditions: cystic fibrosis, sickle cell disease, rare cancers, muscular dystrophies. All of these have been transformed by patient communities that organized, demanded information, challenged medical paternalism, and created pressure for research investment and clinical improvement. Bombay blood has not had this experience, partly because the condition is rarer than most of those, and partly because it does not create the same kind of urgency in daily life. But the same principles apply. An organized community of Bombay blood, individuals and their families, communication with each other and with the healthcare institutions responsible for their care, would be a more effective advocate for the institutional improvements that would protect them than the current dispersed and largely unconnected group of individuals who navigate their condition largely alone, supported by whatever they find in whatever healthcare setting they happen to receive their diagnosis. The movement towards such a community has been tentative and slow, but it is happening. Online forums for people with rare blood types have grown in the era of social media. NHS Blood and Transplant has increased its outreach to communities of people with rare phenotypes. Medical genetics organizations have paid more attention to the patient experience dimension of genetic conditions that primarily manifest as medical risk rather than disease. These developments are positive. They point in a direction that is consistent with what patient advocacy has achieved in other rare conditions, if it is sustained and if the pace accelerates. There is also a generational dimension to this trajectory. The first generation of Bombay blood patients in Britain, those who received their diagnosis in the 1960s and 1970s, when clinical understanding was more limited and patient advocacy was not yet a developed concept in British medicine, navigated their condition in a medical environment that was less transparent, less patient-centered, and less connected to broader patient communities than today's environment. Second and third generation British South Asian individuals receiving Bombay diagnoses today are operating in a different context. They are more likely to have grown up with digital connectivity, with access to international communities of people with similar conditions, with expectations of patient agency that did not exist in their grandparents' medical world. They are better positioned to organize, to advocate, and to create the community infrastructure that would improve outcomes for everyone with this condition. This generational shift is one of the quietly hopeful aspects of the Bombay blood story in Britain. Not that the condition is becoming less rare, or that the medical risks are diminishing, or that the institutional challenges of managing it are being fully resolved, but that the people who carry it are increasingly equipped, culturally and practically, to advocate for the institutional improvements that would better protect them. The expertise exists in the medical establishment. The genetic understanding is deepening. The tools for molecular typing and autologous donation are becoming more accessible. What has been slower to develop is the patient voice, the organized pressure from the affected community that in other rare disease contexts has been the engine of real institutional change. The development of that voice, in whatever forms it takes in the specific communities where Bombay blood is most concentrated in Britain, will be part of how the story evolves in the coming decades. It is not something that the healthcare system can do for affected individuals. It is something that individuals, supported by institutions that recognize their agency and take their advocacy seriously, will do for themselves and for each other. The history of medicine is full of instances where that dynamic, a community refusing to accept inadequate care and demanding something better, has driven transformations that institutional medicine could not have generated on its own. Whether the Bombay blood community in Britain reaches that point of organized collective advocacy depends on many things that cannot be predicted. It depends on the continued development of digital spaces where rare condition communities can form and maintain themselves. It depends on the institutional openness of NHS blood and transplant and related bodies to patient partnership in program design and evaluation. It depends on the availability of peer support resources for newly diagnosed individuals, resources that connect them to others who have been through the same process, and who can be guides rather than leaving them to navigate alone. And it depends on the continued work of research and clinical medicine to understand Bombay blood more fully, to refine the population genetics, to develop the technological solutions that might eventually remove the transfusion compatibility problem entirely, and to communicate findings in ways that are accessible and useful to the affected communities rather than confined to specialist journals that those communities cannot access or read. All of these dependencies are real. None of them are certain. But the direction they point is toward a future where Bombay blood in Britain is managed better than it is today, where more people are identified before rather than during crisis, where the community is more connected and more supported, and where the medical infrastructure is more reliably available to everyone who needs it, regardless of where in the country they happen to be. There is a version of this story that focuses entirely on the science, on the molecular biology and the population genetics and the clinical protocols, and never quite gets to the part that matters most, the part where actual human beings are involved, not as subjects or patients or data points, but as people. People with families and histories and futures, people whose blood type is one fact among the thousands of facts that constitute a human life, important in specific medical contexts and invisible in all the others. The invisibility is worth dwelling on one more time, because it shapes everything about how Bombay blood works in practice. Most conditions that create medical risk are visible in some way. Cardiovascular disease shows up in cholesterol numbers and blood pressure readings and electrocardiogram patterns. Cancer manifests as growth, as symptoms, as changes that investigation reveals. Even many genetic conditions have phenotypic manifestations, features that are detectable in the person's appearance or physiology or biochemistry. Bombay blood has none of these. The person is well. Their blood does everything blood is supposed to do. There is nothing in how they look or feel or function in daily life that suggests anything unusual. This means that the diagnosis, when it comes, arrives in an undifferentiated way. There is no symptom that preceded it, no gradual awareness of something wrong, no period of adjustment to a changing body. The person is simply, one day, the same as they were the day before and every day before that. And then, in the space of a clinical encounter, they are different. Not because anything has changed in their body. Nothing has changed. But because a piece of knowledge now exists that changes everything about how they must think about their body in relation to medical care, The psychological literature on the experience of receiving genetic risk information is rich and varied. People respond to the same information in very different ways, depending on their prior relationship to medical uncertainty, their cultural and family context, their individual psychological resources, and the specific nature of the risk information they receive. Some people experience relief even when the information is frightening, because the uncertainty of not knowing was worse than the certainty of knowing. Others are destabilized by information that restructures their sense of their own body and their own safety in ways that take significant time to work through. For Bombay blood specifically, the response is often described as a delayed reaction. The immediate clinical encounter focuses on practical information, and the practical focus of the conversation keeps the emotional dimension at bay. But in the days and weeks after, as the implications sink in, as the person begins to implement the recommended practices and to tell their family and to think about all the situations in the past where the right blood might not have been available, the full weight of the information often arrives. This delayed processing is normal and expected, but it is not always well supported by the clinical systems that provide the diagnosis. Healthcare workers who counsel rare blood phenotype patients often comment on the particular difficulty of counseling for a condition that is not experienced as illness. When a patient is being counseled about a cancer diagnosis or a serious cardiac condition, the illness itself creates a shared reference point. Both the clinician and the patient know what is wrong. The conversation is about managing something that is already real and present. When counseling for Bombay blood, the situation is different. Nothing is wrong in the present. The risk is future and hypothetical, dependent on circumstances that may or may not ever arise. The challenge is communicating the seriousness of a risk that may never materialize in a way that motivates action without creating disproportionate anxiety about a daily life that is in all other respects entirely ordinary. This is a communication challenge that the clinical training system has not always prepared healthcare workers to navigate well. The generic communication skills that medical and nursing education provides are valuable but not always sufficient for the specific demands of rare genetic risk counseling. The most effective counselors in this space are those who have developed specialized skills through experience, through working with patients who have been through this process, through reflecting on what helps and what does not. These skills are not uniformly distributed across the healthcare workers who are likely to deliver Bombay diagnoses, because the diagnosis can happen in many different clinical settings, not just in specialized genetics or hematology clinics. An emergency medicine registrar at a busy hospital, a general practitioner getting an unexpected result back from a preoperative blood panel, a pediatrician whose patient's extended family typing reveals Bombay phenotype in the child. None of these is necessarily well equipped by their training or their clinical role to provide the comprehensive counseling that a Bombay diagnosis warrants. The referral pathways to more specialized counseling are not always clear, and the urgency of other clinical demands means that rare blood phenotype counseling can be compressed into a very brief encounter when it deserves much more time and care. Addressing this is partly a training issue and partly a system design issue. Training more healthcare workers in rare blood phenotype counseling would help, but so would clearer referral pathways that ensure Bombay patients, once identified, are connected with the specialist services that can provide the full range of support they need: transfusion medicine specialists, clinical genetics counselors, patient support resources, community health workers who can help with family communication. The full ecosystem of support is available in Britain, scattered across different services. The gap is in how reliably individual patients are connected to all of it. The NHS long-term plan, published in 2019, included commitments to improving genomic medicine and to better identifying and managing patients with rare conditions. The implementation of those commitments has been uneven, complicated by the COVID-19 pandemic and by the chronic resource pressures that the NHS faces. But the commitments exist, and they reflect a genuine recognition at the policy level that the NHS needs to do better at managing the full range of genetic diversity present in its patient population. Bombay blood is one specific case within that broader agenda, and it will benefit from the institutional attention that the genomic medicine agenda brings, even if it is not always named explicitly within that agenda. The broader agenda also includes the NHS Genomics Programme, which has built a national infrastructure for genomic testing and data sharing that has no parallel in most healthcare systems. The 100,000 Genomes Project, completed in 2018, sequenced the genomes of 100,000 patients with rare diseases and certain cancers, creating a foundational dataset and a network of genomic medicine centers that are now part of the standard NHS infrastructure. This infrastructure, while not designed specifically for blood group genomics, provides a platform on which extended blood group molecular typing could be built at scale. The technical capacity to sequence blood group genes for every patient in certain high-risk contexts is closer than it has ever been. The economic argument for investing in this capacity, specifically for rare blood phenotype management, will need to be made carefully and based on robust data about the costs of unmanaged rare phenotype emergencies compared to the costs of proactive identification and management programs. That data is not yet fully assembled, partly because the systems for tracking rare blood phenotype emergency outcomes are not sufficiently standardized across the NHS to enable the kind of analysis that would make the economic case conclusively. Building those tracking systems is itself an investment, but it is the kind of investment that pays off by enabling better decisions about larger investments downstream. Everything about Bombay blood management in Britain comes back, eventually, to data. Who is Bombay type? Where are they? What has happened to them medically? How well has the system served them? How many were identified proactively versus in emergency? How many had autologous blood available when they needed it? How many received inappropriate blood before their phenotype was known? These questions are answerable, in principle, if the data infrastructure exists to answer them. In practice, the data is fragmentary, distributed across multiple systems that do not communicate seamlessly, and not always collected in a form that enables the analysis that would drive improvement. Better data would not by itself fix the problems of Bombay blood management in Britain, but it is a precondition for fixing them systematically, rather than through ad hoc responses to individual emergencies. Without knowing how many Bombay patients there are, where they are, and what their medical experiences have been, the healthcare system cannot make evidence-based decisions about where to invest in improvement. It cannot know whether the community outreach programs are working. It cannot evaluate whether the autologous donation program is reaching the people who need it. It cannot demonstrate to decision-makers that the investment in rare blood phenotype management is justified and effective. This is the unglamorous but essential dimension of improving care for a condition like Bombay blood. Not the dramatic science of molecular typing or the human drama of a rare donor flying across the world. Just the patient work of building data systems, connecting databases, standardizing the collection of clinical information, and using that information to make better decisions. It is the infrastructure of care rather than the art of care, and it matters at least as much. The people who do this work, the informaticists and the data managers and the public health researchers who build the evidence base that healthcare policy depends on, are among the least visible contributors to the management of rare conditions. They are not in the clinical encounter, they are not in the emergency room, they are in offices and laboratories and conference rooms, working with spreadsheets and database systems and statistical models, producing the reports and analyses that tell the healthcare system how it is performing and where it needs to change. Their contribution is essential, and it is largely invisible to patients and to the public, which means it is also poorly advocated for when resource decisions are being made. In the context of Bombay blood, the absence of this data infrastructure means that the evidence base for decision-making is thinner than it should be. The estimates of how many Bombay-type individuals live in Britain are precisely that, estimates, based on population genetics, calculations, and small samples, not on systematic population screening. The data on clinical outcomes for Bombay patients in British hospitals is incomplete. The evidence on the effectiveness of community outreach programs is largely qualitative. The economic analysis that would justify investment in proactive screening is based on limited data about emergency care costs. Building this evidence base will take years and will require deliberate investment. But it is investment that will pay dividends, not just for Bombay blood, but for the management of rare blood phenotypes more broadly, and for the larger agenda of ensuring that the NHS can identify and appropriately serve all the patients with unusual genetic profiles that its diverse population contains. The return on this investment is measured in lives protected, in emergencies prevented, in the quiet accumulation of better outcomes for a small number of people whose needs the system has historically underserved. And finally, after all the science and the history and the policy and the community work, this is what matters most: the people, the specific individuals who carry Bombay blood in their bodies, who live their lives in cities and towns across Britain, who go to work and raise families and grow old without ever knowing, most of them, that their blood tells a story that reaches back thousands of years and across continents. The few who do know, who have navigated the medical system and made the practical arrangements and had the difficult conversations with their families, who carry their medical ID cards and attend their annual reviews, and occasionally receive the call from the blood service asking them to come in and donate. And the healthcare workers, the coordinators, the scientists, the counsellors, the community health workers, who have made it their work to ensure that when the moment comes, when someone with Bombay blood needs help, the system is ready to provide it. All of them are part of this story. All of them matter. The blood that connects them is invisible and ancient and present in every moment of every day, doing its work, carrying its history, making everything else possible. It does not know it is unusual. It does not know it is telling a story about migration and genetics and the particular way that human history has deposited itself in the cells of this specific population at this specific moment in this specific country. It just moves. It just does what blood does, which is to keep the person alive. And that, in the end, is what all of this is about. When historians of medicine look back on this era from 100 years hence, one of the things they will note is the period when genomic science and mass migration intersected in ways that healthcare systems were entirely unprepared for. The 20th century was the century in which, for the first time in human history, both the movement of populations and the tools to understand the biological consequences of that movement occurred within the same generational time frame. People moved, science developed, and the combination created challenges and opportunities that neither the migrants nor the scientists had anticipated. Bombay blood in Britain is a small but clear example of this intersection. The people came. They brought their biology with them. The science developed far enough to see that biology. And the healthcare system has spent the intervening decades learning, imperfectly, what to do with what the science reveals. This is not a unique process. It is happening across medicine in many forms, with many populations, with many genetic variants of clinical relevance. Bombay blood is the particularly striking case, the one where the rarity of the variant and the specificity of the clinical risk combine to make the stakes most immediately visible. In the longer view, the story of Bombay blood in Britain is also the story of the NHS learning what it means to serve a diverse population. The NHS was founded in 1948, in the same year that the Empire Windrush arrived, and the same year that the British Nationality Act created the legal framework for Commonwealth migration. The service and the demographic change that would most profoundly test it began in the same moment. Neither the architects of the NHS, nor the migrants who would become its patients in growing numbers, anticipated exactly how their stories would intersect. But they have intersected, for 7 decades now. And the management of rare blood phenotypes like Bombay blood is one of the places where that intersection is most precisely legible. The NHS at its founding was built on a principle of universality, the idea that the same standard of care should be available to every person in the country, regardless of their ability to pay, or their social position, or their background. What it could not have anticipated is that universality would eventually require understanding that different people have different medical needs, that the biological diversity of the human population is real and clinically significant, and that a service that treats everyone the same in a procedural sense may still fail to serve everyone equally well if its clinical protocols are calibrated only to the majority. This is the challenge that rare blood phenotypes have made visible, and making something visible is the first step toward addressing it. The NHS has become, over 7 decades, a service that is more aware of the biological diversity of its patient population than its founders were or could have been. That awareness is incomplete. The systems for responding to it are imperfect. But the direction of movement is real, and it is in the direction that the founding principle of universality actually requires. To care for everyone equally is not to care for everyone identically. It is to care for everyone with the full attention to their specific needs that their specific biology and history and circumstances require. For most people, that means standard care is good care. For the small number who carry Bombay blood, it means something more. It means a healthcare system that knows they exist, knows where they are, knows what they need, and can provide it when the moment comes. It means a system that has done the work of understanding a rare condition, building the infrastructure to manage it, and developing the community relationships that allow that infrastructure to actually reach the people it is designed to serve. Britain has done some of this work. It needs to do more. The gap between where it is and where it needs to be is real but bridgeable. And the people doing the bridging, the scientists and coordinators and community workers and donor families, are doing work that is quiet and essential and deserves to be understood as exactly what it is. Medicine, at its most fundamental. The work of knowing who the patient is, in the deepest biological and historical sense, so that when care is needed, the care provided is the right care. In the end, every conversation about Bombay blood comes back to a person, to the specific individual who carries this rare variant in their blood, who is going about their life without knowing, or who knows and carries that knowledge with whatever mix of practicality and weight and equanimity they have found. To the family members who should know but may not yet. To the healthcare workers who have devoted their professional lives to ensuring that when someone with this blood type needs help, help is available. And it comes back to something even more elemental, to the blood itself, the 4,500 heartbeats per hour, the continuous movement of red cells through miles of vessels, the quiet insistence of the biological machinery on its own continuation. The blood does not know what we know about it. It does not know that it is unusual, that it carries a variant that concentrates in certain communities for historical reasons, that its molecular surface is being analyzed in laboratories and tracked in registries and discussed in policy documents and described in videos late at night by people trying to understand where they come from and how they are connected to the world. The blood just moves, and in moving, it sustains the life that asks all the questions. The life that looks backward through history, trying to understand the present. The life that looks forward into medicine, trying to protect the future. The life that is, right now, listening to this, somewhere in the world, with its own blood moving through it, carrying its own history, doing its own essential work. If you are Bombay type, you are part of a very small group of people whose biology connects them to a particular thread in the long story of human movement across the planet. If you are not, your blood carries its own history, its own genetic record of migrations and populations and selective pressures, less dramatic perhaps in its clinical implications, but equally real in its biological actuality. We are all archives. We are all, in our blood, records of where human beings have been and what has happened to them over thousands of years of living and moving and reproducing and dying. This is what blood carries, not just oxygen, history, not just hemoglobin, the past, not just nutrients and immune cells and clotting factors, the accumulated consequences of everything that has ever happened to the populations that preceded us. It is an astonishing fact, and it is the most ordinary fact in the world simultaneously. Every heartbeat carries both the ordinary and the astonishing, and most of us never think about it at all. Bombay blood makes you think about it. That is, perhaps, the most unexpected gift of this strange molecular rarity. It creates a window into what blood actually is, and what it carries, and what it means. And through that window, if you look long enough, you can see not just a medical anomaly but a story. The story of human movement and human biology, and the way they are inseparable from each other, written in the cells of people living their lives in British cities, carrying in their blood a history that reaches back to the Indian subcontinent and through it to the deepest layers of human evolutionary time. That story is ongoing. It is being written every day, in every heartbeat of every person who carries the H-null phenotype anywhere in the world. It does not have an ending. It has only the next chapter, and the chapter after that, as the science deepens and the communities change and the medicine improves and the blood keeps moving, doing its ancient, essential, extraordinary work. If tonight this story has kept you company in the dark, If the slow unfolding of it through molecules and migrations and medical history has given your mind something to travel through as the world outside went quiet, then it has done what it set out to do. Not to alarm you or overwhelm you, but to open something up, to show you that the world is deeper and older and more intricately connected than the surface of things suggests. That the blood moving through the bodies of strangers in another city carries its own version of this depth. That every human body is, if you know how to look, a record of an unimaginable past. You do not need to remember the name of the gene or the chromosome it lives on, or the year the phenotype was first described. What stays matters more than what is memorized. The sense that rare things have their reasons, that unusual distributions have their histories, that the biological and the historical are not separate stories but one story told in two languages simultaneously. The South Asian communities of Britain are not merely neighbours or fellow citizens in the civic sense, though they are both of those things. They are also people whose presence in this country is written into its blood banks, into its medical registries, into the molecular architecture of its healthcare challenges and its healthcare achievements. That writing is not metaphorical, it is literal. It is measurable. It is there in the lists maintained by rare donor coordinators, and in the frozen autologous units stored in liquid nitrogen, and in the extended blood typing results that arrive on the screens of transfusion medicine specialists in Birmingham and Leicester and Manchester. That is what migration does. It moves biology as well as culture, as well as labor, as well as language and food and music and faith. It moves the molecular record of thousands of years of human history from one place to another and deposits it in a new context where it must be read and understood and responded to by institutions that were built before the movement began, and must update themselves to serve the reality the movement created. Britain is doing that updating, slowly, imperfectly, with all the friction that institutional change always involves. But genuinely, the direction is right, even when the pace is frustrating, and the people doing the work deserve to be seen, which is the most that a story like this can offer them. A small contribution to the visibility of work that is mostly invisible, for the benefit of a condition that is entirely invisible, in service of people whose unusual biology makes them at once rarer than almost anyone and completely ordinary in everything else about who they are. There are stories that are easy to tell because they have clear heroes and clear villains, and a narrative arc that moves from problem to solution in ways that feel satisfying. The story of Bombay blood in Britain is not that kind of story. It does not have a villain. The medical system that failed for a time to account for this rare phenotype was not malicious. It was limited, as all systems are limited by the knowledge and assumptions of their founding moment. The communities that carried Bombay blood into Britain were not tragic victims. They were people pursuing their lives, their opportunities, their families' futures, as people have always done. The scientists and coordinators who built the infrastructure to manage this condition were not heroes in any dramatic sense. They were professionals doing work that needed doing, with the tools available to them at the time. What makes the story worth telling is not its drama, it is its depth, the way it connects things that usually stay separate. Molecule and migration, cell surface and history, a gene on chromosome 19, and the fate of empires. The quiet daily work of transfusion coordinators and the vast movement of populations across oceans and centuries. These connections are real. They are not metaphors. The molecule is actually there. The migration actually happened. The connection between them is written in the biology of living people and in the records of blood banks and in the findings of population genetics researchers. Everything about this story is true, all the way down, from the broadest historical sweep to the most precise molecular detail. That is what good science does when it is working at its best. It finds these connections, it traces them, it makes them visible. And making them visible, naming them and describing them with precision and honesty is how knowledge is built into the kind of understanding that actually changes how we treat people. That is the whole story, or as much of it as we can see from here. The blood keeps moving, and that is enough.